guys hear me okay? There we go. All right, I'm going to wait a couple minutes. I think we're expecting a few more, and if we don't get them, we'll go on. So some of you who have used NoSQL Bench before, this won't be a deep technical session, so it'll be a recap for some of the basics and some demonstrations. So this is primarily geared for people who need to know what it's about, why they might use it, that kind of thing. I was also considering, we have a new version that's in the works based on the Java 21 runtime. If there's enough interest, I may do an online session to get people bootstrapped on that version. So before the end of this, I'll try to remind people to send me an email if they're interested in that. I'll put my email address up there. All right. So of the 5 of you, how many of you have used NoSQL Bench before? All right. I know you have too. That's all right. So you probably know what it's about. It's essentially a tool that speaks multiple protocols that allows us to do testing across different systems, disparate systems, using the same common data set, access patterns, and so on. And we use it every day at DataStax for multiple purposes. And it's an open source project. It's a community project. DataStax sponsors it by paying for its development, but DataStax also benefits from it because we get to use it every day to do light testing or serious testing, depending on what our needs are. I'll wait a minute and recap. All right, so just to recap, it's a multi-protocol tool, right? You know what it is, Branimir. I don't have to recap for you. All right, we'll just keep going. We're going to keep getting people coming in. It's early. So it was based on a few different projects. One of them was to verify that we could do procedural data generation in a way that was configurable by users who didn't want to do development. Called it the recipe-oriented approach. That was proven out by a project called MetaGener originally, presented at the Next Gen Cassandra Committers conference. And the first version of it was okay, it worked. It wasn't that accessible. So the next version, called Virtual Dataset, used Java paradigms a little more directly to allow Java developers to write the functions that can be used. And that was much more accessible and much more usable. Engine Block is just a runtime testing harness that lets us deal with aspects like metrics collection, abstracting the per cycle operations, things like that. And paired with those, we have driver adapters. Driver adapters are like cartridges you plug in to the runtime that essentially allow the engine to speak multiple protocols. If you have an adapter for your protocol, it can speak to protocol. And you might ask why we built it. And originally the answer was very simple. We needed to do a kind of test that no other tool would let us do. It's really simple, monotonically increasing time series workload. And none of the options out there let us do that simply. As simple as it may sound, it was too difficult to achieve, too difficult for users to manage. The tools that purported to do it didn't do it very well. And it was not accurate. The tools that we had gave us mixed results. I tried to verify cycle per cycle that it was giving us the truth of what was happening, and that was futile. It didn't happen. So we built a simple tool to solve a simple problem. And over the years, as we've had to evolve it, we've figured out how to make it do more and more to kind of adapt to the kind of flexibility we need with the multi-protocol testing requirement. Another benefit that we have is that when you have a workload, it's a single file. The runtime to run it is, if you're on Linux, a single binary. And if you're using one of the built-in workloads, it's just built in. It comes with the binary. You reference it by name as if it were on your file system, and it just works as if you had it yourself. So we're going to get through the non-technical aspects of this. We'll get to some demos, essentially, and then we'll have some room for questions. If you have any questions, please remember them. So one of the things that it can do for you actually is to bridge the gap between different testing needs. You have engineers, you have customers, you have users, you have whatever. And if they have a common tool, the concepts become more tangible. People talk about how to do testing using the same language. And that streamlines things quite a bit. When you're trying to figure out how to do a one-off test, you're reinventing the wheel all over again, and that's just a waste of time. And often those efforts give suboptimal results because it takes about 3 or 4 iterations on a testing tool to actually get it to start working the way it should. Along the way, we figured out how to do some pretty cool things. Procedural data generation was basically the foundation on which every other part was built. And you see it says 01 or near 01 over here. That's because we want the testing clients to behave efficiently. We don't want the testing clients to impose on the behavior of the composed system. So what we do is we try to make the testing clients behave operationally consistently, meaning that they don't have a wild variance in their behavior when you change a distribution in your data set. So we employ multiple techniques. Some of you might know the alias method, something called inverse cumulative distribution sampling, things like that. They allow us to essentially make all of our bindings work in fixed time, regardless of the size of the data set you're simulating. We also figured out how to have essentially multi-protocol support using a relatively consistent descriptor language. It's a YAML format. You specify your workload template, which is composed of operational templates and the order, basically the access patterns, the data that goes into them. And if you know the format, you know the format. You can use it for any of the supported drivers. We also made it so that you could script what happens in the testing session. So initially this was Nashorn, and it eventually got replaced by GraalVM. This is one of the examples of the design principle where we have advanced capabilities, but we try to keep them below the surface for first-time users. They're there, they're working, but if you're doing basic testing, you don't have to see them. If you need to do advanced testing, you can. If you need to do something sophisticated, like tell the system to vary the load by hour over a period of time, it's about 4 lines of JavaScript that you can add to the testing scenario. And it's optional. It's there if you need it. You don't have to use it if you don't. I already talked about the uniform workload template, so we'll skip over that. One of the more recent capabilities we've been using more is the ability to stand up a flywheel that's testing, have essentially an autonomous agent in the runtime looking at the way it's behaving, changing the parameters of the test, and doing what we call multivariate optimization. So it's a live dynamic loop of feedback that allows us to do the kind of testing that a person might do over the course of days or weeks. For example, if they're doing a POC, they say, well, I think it needs to be 46 threads instead of 42. And, well, that takes forever. we can automate all that inside the closed loop system now. Some of the core concepts are essentially the workload. It's a YAML file. It describes all the operations and access patterns that you might want to have in your session, your scenario. And the scenario is a sequence of commands that orchestrates a set of activities together, serially or concurrently. And the core active element of a NoSQL bench test is the activity. So activities operate on a range of numbers on the number line, which essentially are the seed values that determine the data and which operation is selected for every single iteration of that particular activity. And it's like a flywheel. You start it running, it uses a deterministic sequence of operations. Let's say you have 5 different operations that do different things that may be related, emulating a client-side or application-side access pattern. Each cycle will plug in different data to those operations, and after it does 5 operations, it'll go back to the top and do them again with another set of cycles and therefore another set of data. And within the cycle, the adapter is essentially the thing that says, here's the op template. How do I want to interpret it? Do I want to make a CQL operation out of it? Is it a Kafka message? Like, what is it? And the adapter is a selector from all the drivers you have. In the upcoming, the development branch we're working on right now and actively using actually is something called the container. And the container is a key element of our advanced analysis improvements. The container allows us to have activities that share an execution context that can be operated, manipulated, and observed by the autonomous agents, or essentially active commands. And it just allows that state to be carried through to different stages of analysis, so you can have different kinds of analysis occurring on an activity that continues to run, and they can be cohesive. I can talk about that a little bit more. If you haven't used NoSQL Bench before, right now, the 5.17 or the stable release is what I would recommend. It uses, you can instrument for all kinds of metrics flows, but Graphite is the easiest, and we've used it quite a bit with Graphite Exporter, Prometheus, and Grafana. If you want to do the latest and greatest, you'll want to use NoSQL Bench 5.21, which is in development. One of the big benefits of that is that it actually lets you have dimensional metrics, which is much more in the way of Prometheus or Victoria metrics, right? It allows you to add metadata to all your metrics in a way that every single bit of your test data is uniquely identified, canonically identified. The linearized naming form in Graphite kind of breaks a lot of that for us. So in 5.21 and forward, we're going to be focused on dimensional metric labels primarily. And as you'll see in some of the examples, if you want to try some of the built-in workloads, you can use these command line options to find the ones that come with it. You can use the copy command to copy them out to a local file, modify them, and run them. One of the first questions we often get from new users is, what are the metrics I care about? So cycles is measured as the outside time of execution from the very beginning of knowing what cycle you're running to actually closing out or retiring that phase in the test. Inside that, bind is the operation of binding a cycle to a native operation. It's the thing that does the procedural data generation, looks at the op template, the way the adapter wants to interpret it, and makes something like an actual CQL operation in the native driver format. After that, the time it takes to submit the operation and get a result back is called execute. So bind and execute occur mutually exclusively one after the other. And within execute, we measure exceptional results separate from, well, we measure all results, but then we also measure non-exceptional results separately. So that's what we call result success. And a common strategy for verifying your metrics or giving you good information is to look at both of these numbers. And if they're the same, you know you have no exceptions. It's always good to have a cross-check when you're looking at your metrics. We also have a retry mechanism built in. There's a very configurable modular error handler that lets you tell the runtime what to do given certain kinds of errors and whether to retry or not, et cetera. And tries is a histogram that records how many tries each op took before it was successful or it gave up. If you say max tries is 10, and you see something that says 10 in your histogram, you know that you have operations that are probably not completing. So why would you use this with Apache Cassandra? Some of the reasons might be obvious, but I'll go through a few here. When you're learning how to use data modeling for optimization or just to understand what the trade-offs are for a particular approach, it's a very easy tool to use for that. You can just build a simple workload in CQL, run it, get some results, change your data model, do it again. And you can even have all the details of your different data models fully contained within your workload, and you can call them out individually so that you can have them all there as kind of an inventory of things you can try, and then you can run them all and get the results and see them all together if you want. Scale planning is one of the biggest reasons we've used it in the past to help customers, particularly who are wanting to do large deployments. We do a proportional study of a smaller cluster. We do some scaling math. We determine what the scalability character looks like. We might do a validation on a slightly different size cluster to just establish the linearity of our math. And then it gives you a pretty reliable measure of what you need to scale up to an arbitrary size. As long as you're careful in how you do the scaling math, proportionality, apples to apples, that kind of thing, it's very useful for that. Also, if you think about the protocol at the driver level as being a demarcation point, then you can do quite effective end-to-end system testing. In that way, NoSQL Bench takes the role of an app simulator. As long as the access patterns and the data you're plugging into it are representative of what you would do in production, it gives you a very portable, very direct and realistic way to emulate that without having to wait for an app team to build a test harness that might not be used again. Multi-protocol testing scenarios are quite useful for a couple reasons. One is, let's say that you want to do an empirical study between different kinds of systems using the same access patterns, using the same core data. You can do that. In some cases, you might have mixed mode or mixed model application designs. You need to do some CQL and you do some web API. Maybe you need to even do some graph stuff. And you can mix all that in the same workload. And the last one, which is emergent, is the closed-loop performance analysis. And I'll show a little bit more about that here. To go to the next section, I basically recorded all these in Schema so we can see them as if I'm running them up here, but they'll be quicker if I just do it this way. So I'm going to do that. Before I do that, and we get into some of the discussion or Q&A, does anybody have any questions so far? I've kind of breezed over a lot of things. So anything that we want to pause for a moment on? No? All right, let's go ahead. So in order, let's see, are we in the right place? Yeah. So this is showing something called an ad hoc command. And I'll talk through these. In this case, this is a command we're running. And can everybody see that okay? Is the zoom level okay? Okay. So we're using a driver called standard out, which it's not an actual low-level driver. It's a diagnostic tool we use. It lets us take the op template as we specify it in our workload template and render it out in string form. So we can say, what is this? Just basically this equivalent of a Java 2 string kind of treatment. But it allows us to say, given the cycles we're giving it and the bindings or the data generation functions we're giving it, what does that mean in terms of data? It's very handy. Some people even use it to generate data for other testing systems, right? And just an aside, if you're using Faker for testing, please don't. It's fake. It's a vignette. It's not data you should be using for scale testing. That's why virtual data set exists. So what this is showing is we have what is considered an inline binding function or inline generation recipe. And this is just a function in Java. The tool chain for the project finds all of these things that are annotated as binding functions, bundles them up, creates a manifest, puts them on the doc site, sticks them in the runtime. They're all available. If you're a Java developer, you can make your own, put the annotation on there, rebuild it. And now you have a new binding function you can use as a procedural data generation tool. But this double curly brace form in this case is showing us that we don't have to name it. We can just use it anonymously in place. And what we're doing is we're specifying a template of an operation. And when you see this template evaluated per cycle, it's not surprising what it looks like. It does what it says and says what it does. As well, you see the cycles, when we specify the same cycles, 5, which is short for 0.5, we get the same result. All of the data generation is deterministic. If you want different data, excuse me, if you want different data, there are ways of doing that. You can choose a different range of cycles, or you can change your bindings. But if you find a problem in a test at cycle 32,462,000, whatever, and it's reproducible because it's data specific, you can reproduce it. You can tell the test to run that cycle only if you want to. You can hand that to a developer. They can reproduce it. That's really handy. And here's an example showing the next range, 5 to 10. It's showing this form here is essentially what we call a closed open interval, just as you might see in a lot of programming languages. And we also see the progress reporter. At any time, it's showing the pending operations, the ones that have not been dispatched for processing, the ones that are currently being processed, and the ones that have been completed. So you have an asynchronous view, and you can customize the update interval for that. And down here, we're just showing a kind of a contrived example of a very large number. Does our data generation function still work? Yeah, it still works. Any questions on this one? Anything you see up there that you want to know more about? All right, let's go to the next one. This is another example, just showing deterministic operations, but it's also showing a little bit more about how we can tap into all the distribution functions available in the Apache distributions, or the statistical, Apache Common statistical packages. And originally we had to do a little bit of hackery to make this work because the previous version was not exposing the density functions needed to derive the lookup tables. But the current almost release version is quite useful. It just exposes them in a more uniform way. This uses something called inverse cumulative distribution sampling, which is what allows us to get the O1 type of performance we need. It by default hashes the input over the long ordinal space, and then uses that as an index into the inverse cumulative distribution function on a lookup table of 1,000 data points per function. And what that does is it gives us pretty close, it's not a facsimile, but it's almost a facsimile of the same data you would get if you computed it by hand every time, or computed it from the function directly. But what it really does is it allows us to do all of these things in the same performance envelope. Different data, same exact operational envelope for the client. And we're showing we have continuous and discrete functions here as well. Here's an example of taking a different approach to defining a workload. We're not doing an inline, implicit one operation template. What we're doing now is we're actually creating a file. And now you see our procedural data generation functions, or binding functions, much easier to say. We have a map. We name them, and we can reference them by name later. So in the exact same statement form, we're not using a double curly brace. We're referencing a named binding, which is defined in our workload template. And we have a set of operations that each has a name, and the operation has details that tell NoSQL Bench how to actually interpret it. In this particular case, we still run it with the driver standard out so it knows how to interpret that op template. There will be an easier way to specify that coming up. This is showing template variables. And all these are available on the link, and I'll make sure you can see that link. You can go and replay them as you like. We're clipping some of the text at the top, but I'll explain. Template variables allow you to parameterize a workload simply by using a macro facility. The macro facility looks at the named variables you provide on your command line, plugs them in to where you have the template variables defined. In this particular case, you see we have this template variable called max value. Here we specify when we run this, nothing, meaning it's taking the default of 100. And this other binding function, which is different than the template variable form you see here, this is a binding function called template. This is just a handy string compositor that lets you put curly braces in as anchoring points for injection. And those pair up just like with a printf with each function. So we're using the hash range binding function, 0 to some value, 100. And when we don't specify an override for that, we get hash values between 0 and 100. But say we want to change the cardinality of a data set in test, for example, we can pass that on the command line, just like this. And now you see the values change. So we didn't have to load any data into any ETL, shadow copy, anything in production. This virtual data set facility makes the mass and the carrying cost of having completely different test data almost free, right? You change the definition, you have effectively changed a virtual data set. You run it again, it behaves as if you had all of that on disk already. I/O is expensive. One of the nice things we learned about procedural data generation compared to bulk testing methods, loading data, is that modern processors are extremely efficient at generating data, orders of magnitude faster than piping I/O from disk through memory to the network socket. You would be surprised at how much, but you'll see an example of that. If you have a more sophisticated scenario that you want to run that may have multiple phases of testing that do different things, or maybe you have a schema phase, maybe you have a load some background data phase. We call that schema and ramp up in our conventions. You can script it effectively using just a command line template. And what this does is it allows you to encapsulate a set of parameters, testing sequence or whatever, in a file. Let's say that you're working with somebody, a customer or developer or vice versa, and you need to speak the same language, have the same exact workload template. It's just this file now, and when you call this file as a command, the name scenario is resolved by what names are defined within it. There was no name scenario specified, just a workload template here. It found the default one, and it ran both of those. So let me actually let it run through again. I paused it so you can see the top. It's unsurprising, right? It looks like what it does what it looks like. How are we doing on time? We all right? So if you want to find the workloads that are built in, and the font size on this one's a little bit small, sorry about that. The -- list workloads option lets you find everything inside that has a certain file pattern and name scenarios. And these are all the ones that you can use out of the box. There are more. These are just the CQL ones. If you're looking at these for the first time, I would highly recommend looking at the ones called Baselines V2, because that's the second generation of our canonical test set that we've used for a lot of different benchmarks. You can see it's easy to get them out and use them, modify them, and use them as if you had written them. It's much easier to start from examples here, because there are a lot of options that maybe you don't want to learn how to use all the things, but you want to be able to use these workloads. So it's good just to take one of these, copy it out, modify it, and run it, and experiment with it that way. And this is just showing running one of those built-in workloads. It's basically doing what you would expect. Now, this is not real time, by the way. The screen recording does let you take out long pauses, and I'm doing that for the time we have. So in real time, this would run over more than a couple seconds. But this gives you an idea about what it would look like. And you see there's no details shown except that it completed, and it shows you how far it got. You can turn up the verbosity. Throw a -v, and it turns the log level up from warn to info. Another -v to debug, and another -v to trace. But usually you don't want all that, because no news is good news. It's designed to be that way here. It's there if you need it. This is just showing an interactive customization of a workload. I'll do the same thing I did before. I just get one of them out using the cat command, similar to the copy command. And when you do this, it's good to name it differently, too. You don't want to wonder which one it is. the built-in or yours. But I'm just copying one of the name scenarios. Instead of using the default name, I'm calling it my settings, changing the settings. And what this means is when I hand this template over to someone else to reproduce what I've done or run the same test, all I have to do is give them the workload and tell them the name scenario. The parameters come along for the ride because we put a customization in there just for that. So here's an example of using an inline command, but also using a thing I recently added called dry run emit. So there's a dry run mode that you can use to wrap some of the internal logic so that you can see what the test harness itself is capable of without invoking any external systems. And this particular mode, we have the dry run equals emit. What this does is it takes the result of an operation, uses the driver adapter's string rendering, and gives you the result. So it's not quite CQLSH, but it's a one-liner and it just works real quick. And if you know how to read it, you get the data you need. It's nice to be able to do things like that to validate testing. Talking about multiple protocols, web APIs are supported. The web API or the HTTP driver is quite comprehensive in the diagnostics you can get from it. It's useful for interactively figuring out how to do web API testing. You can inject your own headers, etc. But more importantly, the payload format is a structural template. We talked about the string templates. Well, the virtual dataset facility actually allows us to do the same thing with lists of maps of whatever, of strings and whatever. And whenever the template is resolved during initialization, the structure is resolved directly. Static values are memoized for efficiency. And whenever the total value of that payload is created, it's stitched together from all the memoized elements. So it's actually quite efficient. It's not just a big text block. But it does show you that you can, let's go back to the beginning here, see if we can see we have full name here. And it's taking this name binding and plugging it into the payload. But it knows that this is a map. And it knows that this is a string template and this is just a string. So something else, this is one of the built-in bindings we had, this full names. This takes all of the names that occurred 100 or more times in the last census that published that data. A lot of different seed data like that is bundled with NoSQL Bench. And this produces a realistic simulation of names that were in that census using something called the alias method. It's quite an efficient O1 sampling method for large data sets with many different weights. But we support using any CSV data file to pull that in and do whatever you need, right? This is showing the listing of the drivers, which some of you might be curious about. Like, what drivers do we support? Let's go back to the top and just look at that. I think. There we go. So there's quite a few in here. If there's a driver that you would like to use that is not there, let us know, but even better, join our developer community and help us build one. The APIs for doing that are pretty well abstracted now. It's not difficult once you do the first one, once you understand how the abstraction layer worked for mapping an operation to a native, mapping a template to a native operation. But it's something we're doing all the time. When we need to test something we don't have an adapter for, we just go build it. And these are all built in. And then here's one of my favorite slides. This is showing the actual O1 effect in detail for the bindings. So we're testing the uniform distribution, and we're running 12 threads. We're running 1 million operations for each one. And then we're doing the same thing with the binomial distribution. And then we're doing the same thing with a normal distribution. And you'll find that they all have almost exactly the same performance envelope. All right, looks like we're at the end. Are we at time completely now? Yeah. Okay. All right, so if anybody has questions further, find me, and I'll be happy to answer any questions you have.
All right, folks, good morning. A small, cozy room and a small, cozy audience. So thank you for showing up for my talk. I know you have multiple talks going on, so thank you for coming to my talk. My name is Arun Gupta. I'm the Vice President and General Manager for Open Ecosystem team at Intel. And as part of that, my team is responsible for crafting Intel's open source strategy. We work with multiple software teams, hardware teams, API teams, specs all across the board to craft that strategy. And today we'll talk about how Intel is working in open source to bring AI to everywhere, whatever device you are using, whatever screen you are using, essentially. So let's take a look at sort of what has happened in recently. Nothing new. This is nothing dramatic, but really, if you think about it, AI is exponentially increasing in both quality and size. If you think about sort of the first transformer model that was done was way back in 2017, about 65 million parameters. But if you see the transition, how it has gone from GPT-2 to 3 to 4, what they're looking at, we're looking at about $1 trillion parameter. This was in 2022, and this is only growing and only gonna grow more. So so the quality is increasing and the size is increasing. So in 5 years only, this is about 15,000 times growth. Where this is gonna stop, and what is the point of diminishing returns? How do you get that compute? What is it that the value that you're getting out of it? That's one element. So that growth has happened, but it is still inaccessible to a lot of developers across the world, whether it's on the training side or on the inferencing side. So if you look at it, for example, on the top it shows the training cost for GPT-3 is $1.65 million, based upon how you're calculating it, if trained on, say, Google TPU v3. Similarly, for GPT-4, it's a $40 million training cost. Not all companies, and this is just a part of it, not all companies have that level of infrastructure, compute processing power, or the dollar amount to get that training going, essentially. And similarly, if you look on the inferencing cost for ChatGPT or Bing AI chatbot, if you're thinking about it, the backend is constantly churning out data. The ChatGPT is a lost business at this point of time because the amount of dollars it takes to run a single ChatGPT query is pretty significant. And that's where the ChatGPT Plus enterprise model, all of those are coming along, just to make sure they can actually make it a bit more sustainable. If you think about, again, in terms of the large language models, what's happening in that space? We started with, say, DALL-E, BARD, GPT-3, 4. The number of parameters are increasing. And it's really driving the productivity to new heights. The innovation is focused more on scaling the AI model size. Is that the right approach? And then more recently, Gemini was introduced by Google. There is Purple Llama, which we'll talk about in a second, was introduced by Meta. Is openness, is closeness a factor in there? Now, how do you make sure that we can build more transparency, build more trust in these models? That's a critical element that Intel really deeply cares about it. These are some of the use cases on how consumers are leveraging AI to their benefit. There is, of course, GitHub Copilot that you use in your day-to-day coding assistance, which is a commodity. But people are building custom copilots where they're able to dig into their network, where they're something like a retrieval augmented generation pipeline, where they're able to dig into their network and their database and make it more custom to their element. Think about the usage of AI for creating hyper-realistic textures. My son is doing master's undergrad and then master's in gaming technologies. So he's deep into gaming and creating those textures and biomes and all. Is still manually driven for his project, but that land is moving towards AI-generated textures as well. I listen to a lot of podcasts. One of the podcasts that I listen to is Hard Fork. It's a podcast by New York Times. And they were talking about how Mountain Dew is using an AI chatbot to go through all the Twitch streams and identify any Mountain Dew branding over there. Whether you are drinking, whether you have a sticker, anywhere Mountain Dew branding is available over there. They get your Twitch ID, they send you a direct message, and then say, hey, you want to be a Mountain Dew ambassador. So that's step one. Step two is where you become an ambassador. Let's say they accept the application, where you become the ambassador, then they continue to monitor your Twitch stream, just to make sure that you have not gone away or walked away from that brand ambassadorship, where you're not promoting the brand anywhere. And then they actually send you a message that, wait, you did not display the Mountain Dew for the last 3 days. Do you still want to be an ambassador? So something as simple as live streaming and what product are you displaying is going to get impacted anywhere and everywhere. And these are like not really large models. These are very custom models, small models, serving a very particular niche, very use case. Now, with that background, let me talk about Intel's legacy in open source. I'm just laying out the landscape here first. But what does Intel do in open source? Intel has a lot of legacy in open source. We have been contributing to open source for over 20 years. Intel is a silicon company, is primarily a hardware company, but there are over 19,000 software engineers at Intel. Several thousand of them actually contribute to open source. And the reason we contribute to open source projects is because our customers consume our silicon, whether in a data center, whether in a cloud hyperscaler, whether in a network or an edge device or a laptop, off-the-shelf laptop that you buy from Best Buy or whatever your favorite retailer is. When you buy that laptop, when you spin up a VM in, say, AWS, you download a latest upstream software, and you expect it to work out of the box in the most optimal manner. So as we are creating new chips, we are making sure there are latest hardware instructions in there. And then correspondingly, we are contributing to those open source projects to make sure those projects are optimized for that underlying hardware as well. So as a result, we contribute to 300 plus open source projects. These are community managed projects. And by that, what I mean is projects like Kubernetes, OpenJDK, PyTorch, TensorFlow, scikit-learn, Modern, LLVM, GCC, Linux kernel. These are the projects where we are one of the largest contributors. And as a matter of fact, Intel is the largest corporate contributor to Linux kernel for over 15 years for that reason. Because as you look into hyperscaler, still the commodity is Intel platform. And as you're looking at Intel platform, we want to make sure all flavors of the underlying distributions, whether it's a canonical, whether it's Amazon Linux, they work. And the best way to make that work is contributing to upstream so that it goes into downstream. So that's sort of our philosophy. We are one of the top 10 contributors to Kubernetes and OpenJDK. And we are also the top 3 contributor to PyTorch and TensorFlow. And the reason we contribute is because our customers tell us that, hey, we want to make sure that we are able to run this in the most optimal manner. More recently, we joined the PyTorch Foundation at the governing board level and the LF AI and Data Foundation at the governing board level as well. Because we believe it's not just doing work in the open source project, but really making sure that the governance, the financial responsibility, the administrative responsibility is about the sustainability of the entire ecosystem. So we continue to partner over there. Let me tell you a story about PyTorch. PyTorch, as we all know, the project was created by Meta. Now, Meta is the primary maintainer of the project, and more maintainers are getting onboarded. Outside Meta, Intel is the only CPU maintainer of PyTorch. What that means is Intel not only contributes patches to PyTorch that makes Intel platform shine for PyTorch, but when others are contributing, whether it's AMD or ARM or other CPU vendors are contributing their patches, Meta and Intel are the only maintainers that are going to merge those patches. And for us, it's really about lifting the entire industry. We don't want to be selfish out there just doing our work. So that chop wood, carry water is a very, very important and essential element for us to make sure we create that impact. Another example on PyTorch is we led significant designs in PyTorch, something like torch.compile. You write your code and you say, go run it. And then we let the design so that the backend is pluggable. Because how torch.compile is going to operate in the backend is going to be different for Intel versus AMD versus any other CPU vendor. So we let that design and created space for other CPU maintainers to be able to contribute over there. So for us, that is part of the legacy. That is critical for us, that as we are contributing to these open source projects, we continue to create space for others and enable them to be successful, because that makes the total addressable market a lot bigger, where more players can compete on an equitable play space, as opposed to locking you into a walled garden where only one vendor contributes, and they define what the innovation is going to look like. Talking a little bit about our open source legacy, as I talked about, Intel is part of several foundations and governing board. Take a look at top left, Kathy Zhang. She is two-time elected member to the CNCF Technical Oversight Committee, which drives the technical direction for Cloud Native Computing Foundation. On the top right is Krob. He is part of the Technical Advisory Council of Open Source Security Foundation and the chair for that body as well. Down at the bottom is Marlo Weston. She is part of the Environmental Sustainability Group. She's a co-chair for the group and defines how CNCF projects could be more sustainable. Myself, I am on the CNCF governing board representing Intel, and I'm also on the OpenSSF governing board, and I happen to be the chair for both the governing boards as well. And that is something Intel supports very well. Like when I was running for the OpenSSF governing board chair, my management supported it. They said, yep, you should run for it. But then I needed somebody to do my internal job, and they gave me additional headcount where they could do my internal work so that I could be that external voice and drive that entire initiative for the industry from Intel. Let's switch gears. Let's talk about what do we mean by bringing AI everywhere. I think it's important that we help the developers realize the full benefit of AI. And the only way they can do that is where we bring AI everywhere, to everyone, to all of your devices, and to all of your use cases. That's sort of the whole concept of AI everywhere. No matter whether you're running it on a client, on a desktop, on a cloud, on an edge, no matter what your use case is, you are training, fine-tuning, running a RAG pipeline, whatever that use case is, we want to support that. And the way we support that is, and the important element is we want to make sure we do that in a very secure, transparent, ethical, responsible manner. Those are sort of the basic pillars on how Intel has operated forever, and think about it. And so the three key elements that we want to think about is, like, how do we help you accelerate the workload with our foundational silicon and the software. That's at the bottom layer. Now, there are general purpose CPU, but then there are targeted CPU, GPU, NPU that I'll talk about in a second from the hardware perspective. On top of that comes is the AI infrastructure, which is where we talk about the projects where we contribute to and how we are enabling those projects for you from whether it's on the cloud or on the client or in between in the edge, wherever you're running it. And then the last one that I'm going to talk about is streamlining the AI workflow to enable seamless development and deployment productivity. Those are critical elements. So let's dig into it a little bit more. So what is Intel's approach? Our approach is really to work at every level of the solution, as you can see here, and enable the best of breed for both our customers and developers. So if you look at the bottom layer here on the accelerate the workload layer here, so we really have a very wide range of hardware, CPU, GPU, accelerators, NPU, neural processing unit that is getting announced, that was announced more recently. So you pick that, and wherever you want to pick it. If you look at your CSPs, those CPUs are prominent in all regions, in all availability zones. You look at Intel Developer Cloud that I'll talk about in a second, where we are providing you the pre-production hardware where you can bring your optimized stack and run them in the most optimal manner. Go a layer above, and that's where we are looking at how are we serving you in the data center or in the client? What softwares are we contributing to? And I'll talk about that in the next slide, essentially. And then with the end-to-end applications, basically doing that in a very open manner where we have this customer-first core value. We listen to customers, then we bring that in, and then we work with them together to create those solutions. So that open participation is important because that's what builds trust, and that's what gives choice to the customers. So really bringing those solutions in an open, choice, and trust manner is critical. And when we look at generative AI, for example, right? When you have several developers, you want to take them, make it easy for them to develop applications. How will you do that? So let's take a look at an overall AI stack that will get you AI everywhere. So again, at the bottom, you have ubiquitous hardware, whether it's Xeon. There are 100 million plus Xeon installed all across the world. So that gives you a lot of compute power that is literally pervasive wherever you are on the compute continuum. So that's one part of it, right? Then on the open software layer, as I talked about, you pick an open source project. As you are building your Gen AI apps, we are contributing to those projects that matter to you. If there is a project that we are not contributing to, we want to hear from you. Tell us what could be different. What do we need to do different? How do we need to engage? That's exactly the charter of my team. Like my team works across Intel, working with these different engineering teams that are contributing upstream, and how are we rallying that together? Then at the top is where all these large language models come in. And again, there are a lot of closed source models happening, but we are a big believer of the open source models here. And so I'm going to share some initiatives that Intel has been driving to make that more successful. More recently, Meta announced Purple Llama. So they did the first Llama 2, but then more recently, Meta announced Purple Llama model, which is an open and a transparent model. And really, the purple really comes from that concept of cybersecurity, where there is a red team, which is an offensive team, and a blue team, which is a defensive team. So red and blue makes purple. So it's a Purple Llama. So they really leverage that concept of what are they doing for red team and what are they doing for blue team, and that's where the name purple comes from. So in the Llama 2 responsible use guide, they recommend that Meta recommended that all inputs and outputs to the LLM be checked and filtered in accordance with the content guidelines appropriate to the application. So really what they're doing is they're announcing something called as Llama Guard, that is an openly available foundation models to help developers avoid generally potentially risky outputs. So you can look at the inputs, you can see what guards need to be done, and then announce it. So on the left, for example, you can see it shows the pipeline here, how you can determine the use case, fine-tune the product, and as you are fine-tuning for your product, this is where the pipeline kicks in, right? That's where you are saying, Purple Llama, what are the safety limitations that you're providing over there? And you keep doing that until you believe that your model is safe. And then again, when you are giving out outputs, at that point again as well, you are injecting the Purple Llama model to make sure the output is clearly safe. So it's really an open project, umbrella project for open trust and safety tools. And we're very excited about this because we've been partnering with Meta on the launch of this Purple Llama model. The other initiative that I want to share with you is the AI Alliance. This alliance was really led by Meta and IBM, essentially. And I'm really excited about this personally because what it gives is a community of researchers, technologies, companies, and end users collaborating together to make sure that the AI stays open, stays safe, and responsible. And in AI Alliance, really, there are three key elements on how do we build and support open technologies across software, hardware, tools, and then how do we enable developers to be successful in it? And then how do we advocate for open innovation? How do we work with the standards and the foundations and the federal government? Because executive mandate came out that, hey, as these large companies are building foundation models, they need to report the results of their pen testing, security testing, all of that to the federal government. So this is really going by that mandate, essentially, that was given by the federal government. So lots of good partners over here. what we're going to do is basically define benchmarks and tools, create evaluation standards for open model releases, responsibly advance the ecosystem of open foundation models, and supporting global AI skills building. Because is how do we grow that total addressable market is a key element as well. Another element that Intel announced earlier this year was the Unified Acceleration Foundation. Now, Intel has had one API, which is basically provides a single API to a range of accelerators, CPU, GPU, NPU, whatever is FPU, FPGA, whatever your underlying accelerator is, so that you don't have to change your application based upon the accelerator that you're running at. And that is Intel's effort of one API. We contributed that to a third-party foundation. This is a Linux foundation essentially. And so we're really committed to open and scalable acceleration. And again, very excited to partner with a bunch of steering members over there. There's a steering committee, and I highly encourage you to take a look at it. Join that foundation if accelerated computing matters to you. The last part that I want to really talk about is the responsible AI, because we believe that it has to be the underlying foundation. We have long recognized the importance of ethical and human rights implications that are associated with the development of technology. The reliance of developers and general customers on the Gen AI technology is becoming so much more prevalent. If this is not done in an ethical and a responsible way, we're really adding a lot more danger over there. So what we do is we address this by utilizing a rigorous multidisciplinary process based on key principles throughout the development lifecycle. Make sure this must be done in a responsible manner, in a very open manner. Open ecosystem is the foundation of anything and everything we do at Intel. And that's what basically drives that entire initiative forward. Just an example of how we are creating that open ecosystem. We have been working with Hugging Face for over 3 years now. Lots of the models over there are trained. For people who don't know, Hugging Face basically provides an open repo for open models, so people can go take a look at it, what model is there, fine-tune it. And Intel has worked with them very closely to encourage that ecosystem more and more. Intel Developer Cloud is again another element. We talked about sort of the pervasive availability of Xeons all across the compute continuum. But Intel Developer Cloud is where you will get to see the latest pre-production hardware. And you can bring your latest open source software and see, hey, how this is going to work on Sapphire Rapids was launched earlier this year. Emerald Rapids is coming. Then Granite Rapids are coming. That's the Intel hardware product line. But how could I run that in a pre-production hardware? And that's what Intel Developer Cloud is. Eventually, once you get it up and running over there, then you can move over. You can either stick to Intel Developer Cloud, or you can move over to a hyperscaler when those hardware components are available over there. But it gives you an ability to test your workload in a very pre-production environment. So I just want to conclude that we would like to be trusted partner in bringing AI everywhere. We want to accelerate innovation with broad AI software portfolio, have that compute ubiquity across the space, whether it's CPU or GPU or accelerator, deploy anywhere and every stage of your AI journey on an Intel platform. We believe we can help you succeed your business. We can help you work with your customers and make it more successful. And this is the last obligatory slide. And that's a wrap for me. Any questions? Thank you. I'm going to be out in the hallway if you have any questions. Thank you so much.
Okay, so hello everyone. Thank you for coming here. I'm Stefano from DataStocks. Today I'm going to show you a library which was built with the purpose of making Cassandra more easily accessible to generative AI folks, which, as you will see, does not always coincide with Cassandra people. So we know that Cassandra 5 is coming, packed with very good new stuff. ACID transaction, SAI, vector search. Vector search. So vector search, in case you don't know it, is a big thing, which is basically the workhorse of this generative AI revolution which is taking place. So looking at the timeline, you notice that CP30, which is the Cassandra enhancement proposal introducing vector support, happened during the course of this year and was very quickly made its way to Cassandra 5, which is about to be released. And you probably know that vector search is a big deal, and so you know vector search probably, but just as a quick reminder, it is a way that it is a search method that enables retrieval of basically anything as long as you can turn it into a vector. In particular, it's very useful for retrieving pieces of text because there are now embedding methods to very cleverly make text into points in a space. And then vector search basically translates the hard task of semantic similarity search into a geometric task. So if you can have a sentence, and you can look for similar sentences, and that has become a problem of geometric problem, which is great because we know how to treat that. So developers, especially generative AI folks, there might be an overlap with people familiar with Cassandra, but you probably can imagine this overlap right now is not that big. And since Cassandra 5 is so great, and it starts to pack support for all of this Gen AI-oriented thing, I think we need a way to enhance this overlap, especially because in this picture, Cassandra and Gen AI people are not drawn to scale. And they are not drawn to scale even in this picture. So generative AI practitioners is an ocean of people. And if we find a way to make Cassandra more accessible, then it's a big win, right? So there is a concept which probably DevRel people know very well, which is the time to hello world. And today, this has to be very short. I'm speaking minutes. Many times, if, let's say, someone lands on your website, on your quick start, and if in 5 minutes they do not see anything working yet, that might be enough to make them flee to someone else, some other vector search database. And we don't want that, right? So raise your hand if you feel familiar with CQL. Of course. We are at the Cassandra Summit. Can you imagine how would CQL feel to someone used to a 2-line of Python code? You can admit it might feel intimidating a bit. Verbose. I mean, I love CQL, don't get me wrong. But we need a way to make at least the time to hello world much shorter, much easier. And this is where Cass.io enters the picture. We want to make using Cassandra easy and quick for folks who don't have time to learn the ways of CQL, but still they want to exploit the various very awesome technologies that are behind Cassandra and its vector search support. So let me show you a quick start. I'm sure you have seen plenty of RAG quick starts. And this is no exception. Actually, this is 2 quick starts in one. So let me jump to, OK, I have a notebook, by the way. Sorry. You will see there is a link here. You can run it yourself, either with Docker, Cassandra 5 beta image, or with DataStax AstraDB if you don't want to get involved with the local running your database. You will find all links in here and in the presentation online. So this is a very standard RAG quick start. I'm not here to show you how RAG works, but so I have already executed the setup steps, which are starting a Docker, Cassandra, checking the contact point, okay, standard stuff. So you see here, this is Python code, of course. This is where I create a session. This is all done. I create a key space, so this is all ready. Now, I also set an OpenAI key for later usage. And now, this is how the Cassio part works. There's one line where I set up a session for later use. Bam. We can skip the AstraDB case because today I'm running with Docker. You can see it here. Docker Cassandra 5.0 Alpha 2. So I can run a CQL just in case it will be needed here. So this is where I create, well, a vector store. It's a table. It's a table directly made the right shape to serve your vector needs, directly made with your indices ready to be queried, and this is everything it takes. A bit easier, a bit more Pythonic than CQL. So, but behind the scenes, a lot of things have happened. Table creation, indices, all that. Then we will populate the store with a few vectors. This is a sample data set with 30-something fake insect descriptions. Let's look at one of them. So there is a name, an order, and a description, like this is some kind of made-up butterfly. So you see, this is how I put my, my entry in the vector store. There is a put method that takes care of everything. It will take care of prepare statements, insertion, everything, schema, translation, post processing, everything. The only thing I have to do is I have to make to create an embedding vector. So this is not a library. This is not LangChain. This is not a library that makes GenAI things for you. This just makes it easier to use Cassandra as if it were exactly the shape of your GenAI needs. So, okay, let me run this one insertion. This is it. So we can maybe just for the fun, we can try desk tables. There is a Cassio demo. Let me. So you see, this is my row. I'm not showing the vector because it's very long. But this is what ends up in the database among other columns. Let me go back to the demo. I want to complete the insertion, so I will compute the remaining embeddings, and still with this Cassio abstraction, run the insertion concurrently to save some time. So that's it. Now, how do you do search? Again, you don't have to deal with the SQL full syntax for vector search, which I'm going to show you later. You see, again, this cell is where the vector search is run, but the vector search is this line. So it's exactly a method built in Cassio, exactly with the shape that you need. So you have a vector, a number of entries, and possibly a metric to measure similarities, and there we go. So I started with a sentence describing some kind of dragonfly. I make it into a vector because that's what I need for running the search, and there we go with the results, or sorted by similarity score. I can do something more. I can run some metadata filters because the appropriate indexes have been built for me by the Cassio table creation. So we are this is only about bugs, and there we go, Coleoptera, Coleoptera, Coleoptera. Again, results. Okay, so the last part of this demo is the full RAG thing. So it's not only retrieval, R, we also want to do AG, so full RAG. And in this case, I think we have seen so many of these chat with your docs things. Okay, so this is a bit different, just for the fun of it. This is a field assistant bot. Imagine you are an amateur entomologist. You spot some insect in the field, and we use RAG to retrieve entries from this fake textbook about biology, and we help the entomologists with identification of the species. So we have a prompt which says, you are an expert entomologist assistant, so-and-so, and then we will stuff this prompt with the observation by the user and the candidate found by the retrieval, just for the fun of it. So I have a function here, suggest observed species, and you see it's basically doing a vector search, then to find the relevant matches according to the observation. Then it formats the prompt template with observation and matches. And then it will ask an LLM to come up with a final identification and degree of accuracy. So this is how it works. I just call suggest observed species with some description. It will, of course, here you see it takes some time, but that's the LLM interaction that takes some time because the retrieval is very fast. And you see, after a bit of text, there is the why and the how this observation matches this insect with a moderate degree of certainty. So this is basically it. Of course, again, I can run it again with a different remark, and I can also run in debug mode, and you will see how the prompt is created. That's, of course, not specific to Cassandra, but it might be fun to see. So this is the actual prompt that is then sent to the LLM, and the answer is, again, based on your observation, because of this and that, this is the insect you saw. So that's it. There's nothing specific to Cassandra here in the RAG part, but that was to give you the sense of how you get all the way to a working application. By way of comparison, I happen to have here a similar notebook with the same application done with pure CQL. And it's nothing extremely verbose, but still, you remember the one line to create the vector store? That's it here. So it starts here, if you do CQL, and it goes all the way here. I'm sure everyone in this room has no trouble doing that. But again, try to put the hat on of someone new to Cassandra. This is a big difference. This fosters adoption, you know. And besides, it already packs the best practices in a sense. It will do prepare statements, it will do optimization, it will take care of all of the right schema, and let's say it makes it more difficult to shoot you in the foot. And the same for when you run the search. So again, this is where you insert, again, some CQL that might scare people away. This is where I do the search, and so on. So this is somehow, so Cassandra has a mission of trying to hide away what is avoidable at least in a first interaction with Cassandra, while keeping the goodies. So Cassandra is more than just a vector store abstraction. It's actually a family of tables, which from a GenAI perspective look like vector store, chat memory, LLM cache, so very specific, and whose purpose is specific to individual typical needs of GenAI application. But actually, what Cassandra does is a more abstract kind of thing. So Cassandra is offering abstractions for a table with a vector, a table with metadata support, searchable metadata support, a table which is just a key value store, and so on. And then you can use them for GenAI purposes or anything, actually. So there's nothing specific to language. There's nothing specific to GenAI, actually, in Cassandra. Indeed, the principles are just to show no CQL unless it's necessary and use the best practices in Cassandra, but trying to avoid showing them to the user unless it's necessary, again. Because GenAI people don't have time to, they don't like boilerplate, like many. They don't have time to learn a new language like CQL, if they can avoid that. And they might like to see their GenAI language being used in the API. But still, we don't want to compromise the good, the best features of Cassandra for that. So we still expose partitioning, we expose TTL, we use prepare statements, and whatnot. OK, so how long do I have? I might spend a bit, yeah, OK. I should be able to spend some time in a bit of dive into how Cassio is structured. So there are basically 3 big modules. One is, I'm starting from the ones on the right. So there is a logic to easily read from several tables at once, doing a client-side join to fill a prompt, typically. So it's a very typical task in a prompt-based LLM application that you read from, let's say, you want to convert a set of primary keys into the actual values you stuff in the prompt, from user ID to name, surname, and date of birth, something like that. So this is a one line to do that. And then there is a config module to easily configure your session before you start using Cassio without having to specify it anymore. But the biggest part is what you see on the left here. And that's a tree of classes built on a base table class, which act like a mixin. So you can mix and match your classes and create the abstraction for your table that suits your needs, no more, no less. So you want metadata or not. You want clustering. You want vector support. You can just mix these mixins, and you will get a table that works. And this is based on a tower of methods that might optionally do something and defer to the higher method in the hierarchy. So let's say the vector table that you have seen in the demo is this metadata vector Cassandra table on the upper right. And that's a base table with vector on top, with metadata on top. So every time you run something like an ANN query, you see this second line in the yellow block, there is the ANN search in the vector mixin, which asks the metadata layer to handle some of the input arguments to make them into the where clause, and then the thing goes back to the vector support, which runs the query, and then again. So every data input and output goes through all the layers, which potentially might have something to say in it or not. So this is how you can get full composability of these abstractions. So where is Cassio used right now? You probably have heard of LangChain and LlamaIndex. These are the 2 most used frameworks to write applications with LLMs. Their support for Cassandra in both cases is built on top of Cassio. And even though users would not see Cassio directly, the rationale behind is that there are so many patterns that are best captured once in Cassio, and then the integrations for LangChain and LlamaIndex are just thin wrappers specific to the idioms of Cassio, of LangChain and LlamaIndex, which just differ for the bulk of managing the table to Cassio. So which opens the way to easy integrations with more frameworks. Not only that, but there is even a legitimate usage of Cassio itself, because not everything is language. I keep forgetting that, but you might have needs for vector search even outside of language, right? So sound similarity, image similarity. You just go straight to Cassio, and you have your ready-made methods to use, like you saw in the demo. Again, easier than doing all the CQL. So the project is evolving. We hope to have 0.2 out very soon. And yeah, you can see here the features that are being added at various stages now. I invite you to go to Cassio.org for quick starts, docs, tutorials, and everything. And of course, it's an open source project, and we welcome contributions and issues and everything. I close by reminding you that if you prefer to work with a cloud database built on Cassandra, we have AstraDB, of course, and Cassio has a first-class support for that as well through a very easy authentication method. So you are invited to try it again. And I think I can stop here, and I thank you for your attention. Thank you. Any question? Sorry, there is one there.
Any plan for like all
Yes. Uh, his talk. Sorry. Yeah, no, Cassandra is Python specific. That was built out of the need of offering something to Python practitioners. There might be, of course, the same can be built in different languages, but as things are now, that would be an undertaking from scratch. But see Jeff's talk later today at 5, right? Yeah, 4:50. There is a very enticing way to cut the shortcut and get to the point of multi-language support. You had a question?
No, I'm good.
Okay. It's okay? Okay, thank you.
Testing mic. Handheld 1. Excuse me, 3, handheld 3.
Welcome, everybody. Hopefully, you had a great coffee break and you're all energized to listen to us over here. So today, I'm Ekta Sachan. I'm a senior engineering manager with Amazon Key Spaces. Today, with my colleague Himanshu over here, we're going to talk about how you can leverage Apache Cassandra to be building highly scalable and efficient AI-based application. We'll be going over, I'll be doing some baselining. What's machine learning? I'm sure you're all very well aware of it, but just take 2 minutes to go over that. Why Apache Cassandra is a great backend system. We have chosen some technologies. One of them is Amazon SageMaker to set up a demo. And the fun part of the talk is going to be with Himanshu over here, who will be going over the 2 use cases and showing some live demos as we speak. So what's machine learning? Some of us, it's really good as humans, some things come very naturally to us. You can look at certain data sets, you can make some observations, you can make some decision. Teaching that to machine is machine learning. Usually in machine learning, you have 2 techniques that is generally applied, supervised and unsupervised. In supervised, you have known input data sets, and a known output data sets, and you do train your algorithm based on that to predict what the outcome of it is. Within supervised, you have 2 techniques, that is classification and regression. In classifications, usually you label the data, and you could actually put it in a normal and an abnormal category and help help teach the algorithm what is within the right pattern. You can use the classification technique to predict the outcome of an event or what could happen in the future. So general use cases for those things would be like, hey, is this an email coming from a genuine place, or is this a spam? Or your bank could use your data sets, or you're doing some transactions with the bank, you have a mortgage, you have a credit history with them. They could use that data set to predict when a customer could go on the default. That's where supervised comes in. There is a similar thing in regression, which is also supervised, but there you're looking at continuous set of data sets to come and teach your algorithm to say, hey, when it's different, how these things connect with each other, and use that algorithm to predict certain things. So a general use case could be about, look at house prices. Hey, the lot size, the dimension of the house, how those are associated, the neighborhood, the number of bedrooms and the bathrooms that could be, how that is associated with the price, and predicting your pricing model for the house is where regression data sets could be used. Now coming to unsupervised side of the technique, where you don't know, you do not label the data set. It's all about the algorithm is looking at what is a common cluster. So that means you actually cluster the data set based on similarities of the object and what's different between those objects. Some of the places where you could look at applying this thinking would be, identifying what kind of customers actually did purchases for a similar kind of product, a very powerful way. There is another technique that commonly gets used in machine learning as well, that is semi-supervised, where you can apply your unsupervised techniques on the known data set, and you can have a better predictive algorithm on part of that data set. Now we would think, where could we be using some of these machine learning? One of the common areas or common problem sets that we could is anomaly detection. Now what's anomaly detection? Well, as human, we can look around and we can say, hey, well, I'm not brightly colored pink shirt wearing a person, but if that person looks different because they're wearing a different color, we could stand out. But that is a data set you could teach your algorithm. So some of the places where we could use this is fraud detection, health monitoring. What's a normal looking image, or what's not. It also can help you find opportunities, like you are in a certain market segment, and an anomaly could be that, hey, we have not penetrated this market. This is a use case that you could be actually looking at building it, marketing it. So it's a very powerful tool that could be utilized in many various places, aspects of it. So now I'll come to say, why Apache Cassandra? We are almost at the end of the second day. I'm sure we all can agree that there are some great benefits Apache Cassandra provides as a NoSQL database. It's a highly scalable system. You can horizontally scale by adding multiple data centers. You could add multiple nodes and scale vertically. That means it can actually provide you very high throughput read and write. That means you could be sending in your IoT data, your log services data, a lot of data munching that you would want to do on some of these data sets. Its inherent architecture, which provides fault tolerance, and the replication actually helps us give confidence that you're not going to lose any of your data. So you could be storing your mission critical data over there and do any kind of analysis on that. Along with all the high throughput, it actually offers high performance with that high throughput. And that makes it really optimal to be using in big data, large data set, to be using on the OLTP side of it, online transaction processing, where you define your schema really well. You can answer your questions really in real time. Or in conjunction with products like Apache Spark, Apache Kafka, Cassandra dataset could be really looked at answering questions for where you have multi-dimensional data sets for online analytical processing. That's what I would say, it's inherently really great. Other benefit of Apache Cassandra, it's not bound to any single product, any single cloud. So you could be in a multi-cloud strategy, you could be in a hybrid, you could be in your own single data center, and you could be looking at that. It's really great. Now, I will quickly talk about certain product choices that we have used in our demo, just to help showcase a product. We've used Amazon Kinesis instead of Kafka to help for the ease of setup, as well as Amazon Key Spaces. Amazon Key Spaces is for Apache Cassandra. It's a managed service which provides a similar kind of scale. It's a compatible Cassandra, so you could be using your SQL queries as similarly as you are using in Cassandra, the same drivers, as long as it is 2.20 licensed. You just don't have to manage your service. It's pretty much that. With that, we also have chosen to use Amazon SageMaker. One of the great service that is the ease of being able to actually choose your data set. Pick and choose your model. It has all those models in there. So if you are just trying to figure out which model is best suited, you could use some of them in there to figure it out. Train it, publish it, deploy it. It just works. One of the great things that I think that was very recently added to the toolkit was model monitoring. While it's really great to be able to set up the model, train your things on it, and get the right prediction, over the period of time, that can change. You don't, certain attributes change. You're not getting that data. Some biases come into the data set. So being able to figure out, hey, how well your prediction is, and being able to adapt to it is very critical as you are working through a long time. So having that monitoring is really key, to make sure that in long term, these things are working well. With that, I know I have given almost a lot of talk over here. Let's get some action. Himanshu, all yours.
Yeah, thank you so much, Ekta. Hey, folks, I'm Himanshu Jindal. So let's go into the demos. So I'll try to do something very brave. I'll show 2 demos in real time. As we speak, I'll run those commands. Hopefully, everything goes well. The 2 demos that we have are, the first is we're going to actually run a recommendation engine using SageMaker. So I'll show you how you can actually train your data, read from key spaces, and actually create segments, and then store them back in key spaces. We'll also do a real-time fraud detection exercise. So we'll actually pump data into Kinesis. We'll see our machine learning algorithm predict based on the training that we have provided it, and we'll insert that data into key spaces. And we'll see all of that happen in real time. So yeah, so let's go straight into it. So the very first demo, it's about a recommendation system, right? So we have a use case where we are a retail company, and we are putting transactions into key spaces, right? So it's a very common use case where if you're a retail company, you want to figure out, okay, who do I send my ads to? Your ads for customers who are very new are likely going to be different from customers who have been using your products for a long time. And very different from customers who haven't used your product in a long time, right? So they haven't come to your store. Maybe they were using it before. So we are going to be using a technique called customer segmenting. And for this example, we use a very simple model to segment our customers into just 5 segments so we can see what kind of ads we can send them. So we'll basically read the transactions from key spaces, segment them, and then run them on, store them in key spaces back. So, all right, so let's see how this comes together. Mirror the display. All right, we're live. So yeah, so we have this table here where so we have this table here already created, which contains a lot of transactions for our customers. So let's just take a look at that table, right? So it contains invoice, it contains stock code, country, description, and we have about 20,000, entries over here. So what we do with SageMaker is I have a lab created already, and I have this command stored. So what I'm doing here is I'm loading this data into SageMaker. So if you see here, I'm establishing an SSL connection to key spaces. I'm selecting all the schema. I'm selecting the data from that schema. And then I'm basically munging the data over here. And you can see there's a lot of comments over here because as you're building an algorithm, you want to remove all the nulls, you want to add data, you want to enrich that data. And then I'm creating a recency frequency monetary score of it, which is a base of how recent the customer has come to your store, how frequently they're coming to the store, and how much money they are spending on your store. And then I'm running k-means clustering on it. And then I'm storing data back to key spaces. So I'm going to change this run ID to something unique, let's say 121, and then run this algorithm. So it's running. Yep, so it has segmented. And it takes a little bit of time to process that and put that into key spaces. Yep, so now we go to key spaces, right? So we have this tables here. Yeah, so we have this ML clustering results table here, which we can query and see. And you can see there's, for run ID 121, there's 5 segments created, and it's the number of customers here. So if we wanted, we could send them targeted emails or different emails that we wanted to. Right, so yeah, so that's the first demo that we have. It allows you to segment customers. But as you were seeing, let me just make sure we can see this. Last video, 1 second. Oh, that there, so we got it back. Yeah, so now that you saw how we can actually segment our data, now let's see how we can build something real time, right? So let's say we are a bank, and we have these transactions coming in, and we want to see how do we detect fraudulent transactions in real time. So the number one piece that we need to build is we need to build a model that can give us real-time results to tell us if a transaction is fraudulent or not. So we have used the service Amazon fraud detector to train a model. So we took an annotated data in S3. It was about 200 megs in size. We trained the model using Amazon fraud detector. It took about a few hours. But once we did that, we have an endpoint which we can call with our data, and it will give us whether it's a fraud or not. So now that we have that model, how do we actually use that to build a real-time system and build a workflow that we can just deploy, and it is totally serverless, and it's just, we don't have to worry about it at all. So the first thing that we'll do is we'll take our transactions and we'll put it into Kinesis. Kinesis is a managed serverless streaming service. So you can put your data in, and you can get it back, and you can put multiple processes on it. So here we're going to put a step function workflow on it. Step function is another serverless offering. It allows us to do orchestrate serverless workflows on events that are coming in. So in this case, we have hooked a step function workflow onto our transaction data stream. And then what we'll do is we'll perform inference using the model that we just trained. And then we'll store those transactions in key spaces. And then we'll send those, if the transaction is fraudulent, then we'll send a notification to SNS, where we can take actions like we can say, if the transaction is over $1,000, then send a text to someone or send a notification to a customer support person. We'll also extend this use case to replicate this data to another AWS region. So imagine you have a use case where you're storing these transactions, but you want to provide 24/7 support to your customers. So you might want to replicate this to, I've replicated to India, for example. So they can also access this data and act on it. So if there's a transaction that's fraudulent, they can see, they can call that person, they can maybe fix those or put some notes in. So yeah, so that's a lot of services. And so let's see how they actually play around in a demo. Nice. Yeah, so let's see. So let's work from our building blocks, right? This is the fraud detector model that I have that I've already trained using fraud detector. So I have a detector here. You can see it was created 4 days ago. And here's the model. And it's trained. And there's basically 3 rules. There's basically it assigns a score. And if it's above a certain number, we're like, OK, this is a fraudulent. If it's between certain numbers, we aren't sure. So we say we are unsure. And if it's less, then we're like, OK, we approve this transaction. And for this example, what I'll do is I'll use Kinesis data generator, which if you haven't, I recommend this tool a lot. It allows you to simulate, to put in real-looking data into Kinesis. So I will actually show you how to create a template that puts transactions that look like real transactions. So, sign in. All right, so you just select your region, and you select your stream, and you specify the rate here. And here's a template. So I'm saying, hey, we've created a transaction ID with these ranges, timestamp a customer email. So I create like a record, and then I can like test my system and see how it works. And here's the state machine that I have. And I can even show you the definition of this. So we can see here that this state machine is first it's calling a fraud detector to get prediction on it. Then it's calling a Lambda to store that transaction in key spaces. And then if it's a suspicious transaction, it's sending it to SNS. Otherwise, it's just ending the state. So you can see it's all just configuration, very easy to deploy. And actually now, let's see how it actually looks like in action. Send data. So now it's sending data. And you can see I already have events coming in here. And I have my key spaces table here where I can select my bank transaction. And you can see it's getting filled up. So, yeah, let's run this. Yeah, so this is in my US East 1 regions. All my resources are in US East 1. And you can see here 311. These are the latest one because it is 311 right now. So yeah, and we can see in our workflow it's running. And if I refresh, there will be many, many more which have been executed. So yeah, as you can see, it's just running in real time and is detecting some of the transaction as blocked. Some of these need to be investigated. Some of these are approved. Yeah, so as you can see, it works in real time. And what we'll also do is, I'll also show how these are being replicated. So this is my Bombay region. So I didn't have to do anything. These are just being replicated to the Bombay region automatically in real time. Yeah, so it's all serverless. Yeah, and the machine learning algorithms that we've used are pretty simple. If you are into machine learning, you can really make these more advanced, train these, and as Ekta said, you can then monitor your model and then improve on these models as well. All right. Mirror. Stand. Okay, all right, we're back. All right, so yeah, these are the links for the demos that I performed. And yeah, you can even ask me any questions or anything that you have. Yeah, thank you so much. These are contact information. Yeah, these were the talks that we did. So thank you so much, folks. We'll take any questions that you have.
Thank you, Himanshu, and thank you, everybody.
Yeah.
So I had a question. Hi. So our team currently actually uses Cassandra as our main data store, and it's a part of a data pipeline. And right now we don't have any machine learning components, but I think many teams are always kind of thinking of, as the next step, how do we integrate ML, right? Just like how you guys do. But the challenge I think comes in that Cassandra really depends on how you design the data model, and that really can. It changes how the partitions are created, and then that affects read and write throughput and all of that, right? So when you created your products, did you have that machine learning component in mind as well as the client endpoint in mind? And did that kind of change how the data model or partition design occurred, or did you have to make any tweaks? I'm just kind of curious about your experience.
Yeah, I think I would say for prototyping, the schema is less important, right? Like your most important goal here is to show that you can provide value to your business. So one of the things that I'm doing is I took a subset of records, so 20,000 out of a big data set, and I ran clustering on it. So I would say the first step should be to just see how you can get value out of that data. So you can show to your business that, yes, by running this algorithm using these tools, we can get data out of it. And then once you're going to scale, then I would look at, okay, for machine learning, I need this schema, but for my reads and writes, I need a different schema. So if there's a different schema, then you can think of creating a replica. You can build a model like we did with, in my second example, where there's a stream and you can put it into two places. Or you can also use Apache Spark to run a job every few hours to just take that data and put it in another place. Then I would look at the cost analysis and see how important it is. And depending on how big your data is, schema might not be as big a problem. But if it's a big problem, then you can definitely consider one of those options.
I will add, Cassandra is a NoSQL database. So actually, defining your schema, especially if you're going to look at real time. So everything that Himanshu added, if you're doing analytical processing, that means that you're munging that data after the fact. Yeah. You could read it with Spark or anything, or could you store it in a temporary setup, right? And analyze the data based on that. But if you're trying to answer more real time, your schema really matters in your NoSQL configuration. So I would say, and storage is cheap. That's the whole thing, right? NoSQL, that's where we have gone to. So having a copy of that same data in multiple forms makes it more efficient, and that's the core behind it.
I add one more thing, just kind of repeat what they said, that in reality, you want to use key spaces because you already have existing data. I would not recommend you use key spaces if you try to do brand new project and you know that you're going to use for just ML, for analytical processes. As I said, in this case, you take existing data from key spaces, create your data lake, create some other processes that will provide you. But if you want to get data from existing schemas, yeah, and this is the best example. And again, one thing that you,
No, go ahead.
just from the cost perspective, you pay for each read. So for the ML process, sometimes you need to read the same data multiple times. And sometimes benefits, again, just build some process to extract the data, and we have multiple ways of extracting data. Store it in the S3, store in your data lake, and use this as your primary one. Any other questions?
If not, thank you so much for coming. It has been a pleasure to have this opportunity and share some of our learnings.
Yeah, thank you so much, folks.
So good evening, all. Glad to see all of you here, and thanks for joining us today on this call. So the topic we are discussing is our journey with DataStax and Cassandra over last 6 or 7 years. And also we didn't just want to leave it high level, some tips for users who are actively using Cassandra in their own environment, especially with focus on the recent DataStax Astra deployment. So this is the team who worked on the presentation. So myself, I'm a co-founder and chief architect at Alpha Technologies. We have Tim, who is the data engineering manager, and Ranjit couldn't join us. So what is Alpha Technologies? What do we do? It's a company founded in 2017, and we have about 400 plus staff, development centers in US, Singapore, India. We transform the maritime. We build IoT platform for ships. We track sailing ships. We have a platform where all data from various machinery on board ships is captured. So there are some servers on the ships, and there are servers on Amazon Cloud. So the data is collected from various machinery, and we transform it, collate it, and send it to the cloud. We use this data to drive various solutions for stakeholders, so which include modules which help ships reduce emissions. So there is a big drive on decarbonization because of the IMO directive to reduce emissions and achieve net zero by 2050. So this is one of the objectives we have. We also do have various other modules which help things like predicting machinery failures or alerting users so we leverage AI and ML to a large extent to drive a lot of our solutions. So tech stack, we are on to Node.js, Java, Angular, Python, Amazon Cloud. We use Cassandra database, and recently we have moved to Astra. Data warehouse is on Snowflake. For DevOps, Azure DevOps, observability, New Relic, and CloudWatch. That's our stack. So just a summary of what we have achieved, about 230,000 metric tons of carbon dioxide saved, 75,000 metric tons of fuel saved, and $38 million of revenue saved for our customers. These are our products, so Smart Ship, Smart Voyager, and ShipArm. So this is in summary. I just explained in brief already, but there is a ship, or shown in the diagram. There are multiple ships like this. So we currently have about 450 ships using our software. So the software on board is accessible to the crew. They can use it. The connectivity from ship to shore is over satellite. It's particularly bad, so we have to do a store forward mechanism to make sure that the data syncs correctly. Now on the ship, we collect about 3,000 to 5,000 data points every 30 seconds from various machinery. Now there's a lot of challenge in the shipping space because it's a niche area. There are very little standards. So every ship is unique. The machinery itself, even though it's the same machine on 2 ships, they follow a different format. And we had to write our own parsers to parse this data. So once the data is retrieved from the ship, we have some parsers sitting there. We have a local database for the application to run, and even when the connection, like the satellite connection, is offline. And then the data is synced to the shore. And on the shore side, the whole data is aggregated. And so a lot of our solutions run on like the optimizations and ML algorithms on the cloud, run on the cloud, because the compute on the ship is not sufficient to perform this analysis. Some of it, smaller ones, run on the ship itself. So why did we go with Cassandra? So one of it, the main aspects is performance. So we do need a high write throughput. Hundreds of vessels are sending roughly 5,000 data points. High read throughput, large number of concurrent users and service requests from even AI, ML algorithms and other services requesting the data. Cassandra is able to handle this with ease. High availability. Now, of course, this is used by various stakeholders, including ship owners, operators. To some extent, the owners, operators, and other insurance providers and few other stakeholders who make use of this data. So it need to be highly available. It need to work on off-the-shelf rugged hardware. We didn't want to procure very specialized hardware or anything on the ship because it has to scale and it has to be reasonably priced. It has to scale on the cloud for future. So even though you would have noticed like the number 500 ships is not large, but the whole shipping, if you look at it, there are roughly 55,000 ships of commercial ships which can use a platform like this. So we already have a decent market size, and so that it's considering the standardization and all that, it has been a challenge to even scale up to the number we are currently. So it's going up much faster at this time. DB replica. So considering the ship and shore disconnect, we had a challenge that on the ship and on the shore, we have to use the same database. This also has the advantage of limiting development, duplicate development for another database to be on the ship, which is lighter. So we had to use same DB on the ship, same on the shore. Now, which other DB can be the same? It can scale. It has to be redundant on the ship. So while we need, when we say redundancy, there has to be multiple nodes. And for some of the other NoSQL databases, you need a separate leader. And the leader has to be highly available as well to have redundancy. So that would all increase the cost. With Cassandra, it's a masterless database. It can have a minimum 3 is what we need, and so that's the reason Cassandra suits this. Cloud agnostic, we can go to any cloud in the future. It's low risk. When we started in 2017, Cassandra was pretty much accepted by leaders, mature technology. So that's the reason we went with Cassandra to begin with. Our Cassandra journey. When we started, we had like roughly 5 engineers. Although currently we are 400, we still, our DevOps and database team is pretty lean. So we hardly have 5 engineers altogether. So when we started 1 DB admin, we selected Mongo. And Mongo wouldn't work for us. We realized it pretty soon. And so, specifically because of the masterless requirement. And then we moved to having our own on-prem data center with Cassandra, with our custom scripting for backups and other custom repairs and other operations were being managed by our own scripting. Of course, with the open source support. Monitoring was quite rudimentary at this time using CloudWatch. We had 1 product, roughly 50 vessels, a single 3-node cluster, about 750 gigs of data. In 2020, we grew to 200 vessels, roughly 10 clusters, 3 to 6 nodes, several TBs of data. Still 1 DB admin, and at this time we have already switched to DataStax Enterprise. The reason was we were finding it challenging to manage the cluster using our own scripting, there were some risks we identified on security. People doing handwritten scripts, keys were hard-coded. Scripts wouldn't sometimes work, things like that. So a lot of challenges, so we moved to DataStax Enterprise. And then 2022, we are already 1,600 plus vessels across different platforms, 3 products. So we have 20 plus DBs, and this is the time when we decided that we'll move to Astra, because it's serverless, it scales according to our need. You don't need too many hours to be spent on creating and managing the cluster, etc. So that's where we moved to Astra. Now, what were some of the challenges we faced as a new user of Cassandra? Cassandra, everybody knows, is a very powerful database, easy to get started, but it becomes painful when you have to maintain it and when the data load increases. So we made our fair share of mistakes. The first set of issues we faced is poor schema misconfiguration, performance issues leading to failed queries, unstable cluster. Nodes would go down at times. We wouldn't, like if there was a heavy query coming in, it would cause a particular node to shut down. And then, the ops would have to look into why and, bring it back on and all that. But all of this was impacting our business. We had random outages at times. And this was also partially because of our poor monitoring capability. So we did have some basic monitoring from the open source using Grafana and all that, but it was still not sufficient to the extent with the limited resources we had. This led to extended resolution times. This also had business impact. Next was complex operations. So when you set up a cluster for Cassandra, you don't really think about all the other aspects which has to go along with it. So you have to repair the cluster. If a node is down for a certain period, you have to bring it up and repair. You have to make sure that all the nodes are in sync. So all of this was being done using our custom scripting. And this was resulting in wasted man hours, security, compliance, governance risk. Again, support, community support, which is somewhat ad hoc in nature. If there was an issue really which we couldn't identify, we had to go to the community and ask questions. And sometimes, we wouldn't get a proper response or a timely response. And this also had a real business impact. So this is where we moved to DataStax Enterprise. We had a session where we decided to refactor our schema to a large extent with DataStax Consulting support. So they identified or helped us identify some of the issues. They clearly understood our use case, and we refactored some of the major blocks. And that led to a healthy cluster, and eventually we moved into the DataStax Enterprise product. So Ops Center is a big thing which comes with the DataStax Enterprise tooling. And that helps you do monitoring and troubleshooting as well as cluster management. So setting up a new cluster, monitoring it, repairs, health status, alerting, all of this is taken care by the Ops Center platform. Ad hoc support, of course, 24/7 enterprise support from DataStax was extremely useful for our team. So if there was an issue, they would come online on video calls and support us through. If there was a real hot issue happening, production outage, things like that, we would get immediate support from all different time zones, which was extremely useful. Now, recently, we moved to Astra. Why Astra from DataStax Enterprise? So one of the challenges, it says pay-per-use, but one of the challenges we had was setting up these clusters for demo and sales, and so there are a large number of clusters which are not really production grade, but Cassandra itself needs a certain minimum size and resourcing to operate properly. And so we would have a 3-node cluster doing very little, and we would have wasted these resources just so out of the 20 clusters, maybe 3 or 4 are production grade. The others are wasting resources just for nothing. So, but with Astra, you pay only for the amount of reads, writes, storage, and data transfer. So that's a big advantage, and we decided to go there. Rapid time to market. So setting up a cluster involves a lot of hours. Even with automation, you have to make sure the cluster is healthy. Looking into best practices, security setup, certificates, everything. By the time you provision a cluster, test it and make sure it's at least a day to 2 days spent by 1 or 2 engineers before it's available. But with Astra, it's you just go in, click, type some configuration, just click, and it's provisioned immediately. Few minutes is all what it takes. Scalability. So Astra scales horizontally, beautifully, very fast. So you don't really care about scale anymore if your schema is optimized appropriately. There are some minor changes we had to do to adapt to Astra, because Astra has to is to be used by a larger number of users. They have to put in guardrails and to avoid misuse or abuse of the system. And so that is in fact a blessing in disguise for our developers to start following the best practices, which actually makes the server or the platform stable for the future. So when we have more users, more scale, and more clients connecting and making requests, all these guardrails help our system. So security and compliance. So with Astra, it's inbuilt, baked in. So you just follow their standard practice, to connect. And so there is data is stored at rest, data is stored in transit. And you can have your own custom key if you want. You can have VPC peering. So the data never, even while it's connecting, it doesn't go over public internet. It connects through a private tunnel. It's cloud native. If you look at the on-prem, it really, if you connect a Cassandra cluster to a big data pipeline, or some other service. So you have all the other components of the pipeline which can scale. Like let's say you have Lambda, you have EKS, Fargate, all of that scales, but the database doesn't scale. Now this gives us the option to scale the database also. And so it's cloud native in that way. You don't have to think too much about sizing the machine and capacity planning and year over year. Spending time on all that. So fully managed, you don't think about a lot of the aspects of manual management, repair, monitoring the nodes. So specific issues, we get alerted by the customer support team. And when there is a real issue, they are on top of it supporting us. So it has been an excellent decision in our view to move. We have in fact saved some and also made a lot of our resourcing available for other tasks. So what's the result and impact? Less operational overhead, no scaling worries, low latency, high throughput availability across workloads, replacing oversized clusters with serverless database, security best practices on each cluster, no variability by environment, best in class support, no more tarballs. So one aspect we observed is when our deployment team sets up the cluster. If it is a production cluster, they would have a certain standard for security or for configuration. But if it's non-production, then they have a different take on the security needs. So all that is gone. It's all production. So Astra guardrails. So it follows. It sort of. So the difference between Astra and some of the other managed service providers, like Keyspaces, for example, is what we have monitored. What we have noticed is that Astra is a bit more flexible to your needs. So sometimes you need X number of tables, or you need some flexibility in the guardrails itself. And DataStack's team have been reasonably flexible to accommodate those needs, which are really genuine. So it has helped our team. Even though there are guardrails, they are not really tight, as in if it's really needed and it's a genuine use case, they are also flexible. Innovation. So over a period of time, since we started using, they have come up with different products. For example, CDC, Astra Streaming, change data capture, vector search for RAG, etc. So in our case, we are still starting to explore the vector search in some of our internal use cases, but we are already using CDC and Astra Streaming for certain use cases. So for example, we had an application where we needed to move data to Snowflake. And so with Astra Streaming, we were able to directly connect Snowflake and move data out without having any external components. So just direct connect into Snowflake and some a little bit of code. It starts writing code. As soon as data comes into a table, that's available in Snowflake for you to consume. So that's just our journey. And so we wanted to leave you with few tips for Astra, some of our lessons learned. And Tim will walk you through those. Thank you.
Thanks, Raveen. Yes, so as we evolve from Open Cassandra to DataStack Enterprise to Astra, there's a few examples that we came through and we learned over it. Our use case mostly evolve around the time series data. So we have a few to share here. So from left, so there's a few options that we have tried. The focused requirements of our time series is that we want to minimize the cluster resource requirements, right? Bias for the right performance. We want to make our schema future-proof, right? Flexible. So with that, we want to look at the option how we arrange the schema, the data model to support these requirements. So the first one on the left is, sensor to have name and values as a pair, right? So the first option is that each row will have a tag name and a tag value, right? So we try that. The good thing about it is that when you have fewer tags, right, the selection will be pretty quick, and it serves the purpose. When you know what tag that you want to get, right? It gives you directly that value because it's right there in the row. The downside of it is that because each rows have just one tag, right? We want to support 3,000, 5,000 tags for each 30 seconds, so that's a lot of writes, right? And that is not what we want, right? Another downside is that if you want to query across multi-tags, right, you have to gather all the rows for all these tags, right? So that is not optimized, right? The next one is we consider the flat model, right? So instead of each row have each tag, we put more tags into one row, right? And then the key we arranged by group source, right? So sensor, we're grouping them, and source is another instance that belongs to that tags, right? So when you query, you can query by source name on the date that you want. So you get the rows, you get back a list of tags, right? So that is a little bit better than the row. Each row has its tag, right? It's more dynamic. You can get more various tags on one row. But then the downside of that is that we have a lot of tags for each vessel, so it's end up like a lot of columns, right, on the table, and that's another downside. Yeah. We try another one is collections, right? Instead of having a flat table, flat row, we try to do like map collections, where you have a pair value inside. You can even put index in the map. And with that, you can, instead of having, so you can overcome the wide table. You have only one column where you have map and value. So then when you query a row, you can look up by tag name. Right? So the good thing is you don't have the wide table problem. But then you have to deal with the collection, right? So when we go and test it, the performance result of having collection, it doesn't really meet what we want, right? 3,000, 5,000 writes per 30 seconds, right? And then the last one we try, right? Instead of having collection, we have a string representation of the map, right? It's in text, and that achieves what we want. It's simple. It's a compact structures. It's future-proof. If ever you want to change the structure in that collection, right? A string representation is free-form. Right? You don't have to change the schema. One thing about Cassandra, when you don't want to change schema, right? You want to go back history, and then you have to fix all of that data migration. That's a lot of problem. But the downside is that with the free-form JSON string, you got when you read it, you gotta unparse it into JSONs on the clients. That's a kind of downside, but that's why the client side, they know what they want, they know what they put in, they know what they get out, so that's okay. Another downside is that. Yeah, if you want to get some specific tags out of that, it's maybe a challenge because you have to unparse the JSONs and get to that, right? So, so we chose the last one, and here we did some kind of performance tests on option that we have. So the first one is insert for flat collections and the text string, right? We take about 20 tags, and we test that. And on the right, you got the time that for this test we have. It's come out that the long text string takes only 49 milliseconds for write 20 tags. Right? On selections, the long text string is the winner. It's only take 9 milliseconds to read that string of text. Okay. Another lesson learned we have is that we have some tips for improving performance from the traditional OpenStack to Astra. With the traditional Cassandra, we deal with the parallel queries by using batch inserts, and then we have this range selection queries, as you see the example below. Where you want to write using batch. There's a limitation there we have, which Astra, we don't have to deal with that. We can have many inserts going in parallel and let Astra dealing with scaling on that, so that worked well. Same thing for selections, right? Instead of you do an int statement, you can send multiple selections. Okay, so moving on. There's some tips on improving cost efficiency. Yeah, so we have issue on, we have too many reads and writes and updates. We have a lot of data size, right? We have different approach by doing caching. We recompile the S3 into a file, right? Instead of reading on the same table, repeating reads, we do computation and we write to S3 file. And we have an API just open that S3 file and streaming back. We also done compression for large size of data. Okay, let's moving on here. Last one, data migration strategy. We try different approach using CDM, Spark, DSBO, and there's useful for each. There's limitation for each also. Okay, so for CDM, it's useful when doing both the time series migration. You don't have to do a lot of coding configurations. It's fast, reliable when you do transfer data transfer. Right? But the downside of that is we have issue. We run into issue with table columns, which user define type when the destination key space are different. Right? That's right. Yeah, I think we're running out of time. We leave this on the slide. You can look at it, and if you have any question, we always be here. Okay. Thank you.
Okay, I think we're live. Are we live? We're good. Yes, okay. Greetings, everyone. We are here to talk about enhancing Apache Cassandra drivers with vector support. Pretty much what it says on the tin. Quick introduction, just so you guys can know you're not talking to somebody, just a random face. My name is Brett McGuire. I have worked at DataStax for almost 9 years now. I've done a number of different things while I've been there, but I have recently been doing a lot of support and development for our various native driver offerings for the past 3 or 4 years, somewhere around there. And I am currently a member of the Astra Connectivity team, which for those of you who, I don't know if anyone was just in the room next door, we were talking about another one of our products, ZDM, and we cover a wide portfolio of offerings at DataStax, including the native drivers, ZDM, DSBulk. We cover a lot of things. But enough about me. This is a rare opportunity for me to actually find out information from the field, from some of our users who are actually using things. I write a lot of software and ship it out into the world, and then it goes off, and our wonderful support people give me feedback. But I always like to sort of get this information directly from people. So DataStax current# maintains 5 active drivers that we offer support for, including those are drivers for Java, Python, C#, C++, and I'm forgetting one, Node.js. There it is. So I just a quick show of hands. Don't worry, I'm not going to interrogate anybody. Jeremiah is excluded because I know he already knows the answers to all of these things. But out of these, how many, for folks who are in the room, which of these drivers have you worked with? How many people have worked roughly with the Java driver? Just rough show of hands. Okay, quite a few. How about Python? Any Python takers? Still pretty good representation. Okay. We'll kind of lump the other 3 into a larger bucket. Maybe we can interrogate them individually if we need to. But C#, any C# takers? Oh, okay, excellent. We know a C# taker. Node.js? Steph? So, kind of. A little bit. Okay, that works. And C++. Any C++ takers? Well, I should have known. So, okay, that kind of matches about what I was expecting. Out of the folks in the room, so my next question for out of the folks in the room, I know people have used, or it sounds like people have used the drivers and have used some of the APIs. Does anyone here, and I'll exclude the core developers who I know already know the answer to this. Does anyone here have any experience or have spent any time looking at the binary protocol that the drivers use to interact with the servers? Piotr, Jeremiah, keep your heads down. Anybody else? If not, that's okay. It does come up a little bit in our talk, or in the talk here of things that we need to review. So I'll try to mention those. But as mentioned, we won't go into too much detail because it can be a little intimidating when people first meet it. So we'll cover just enough of it to kind of move on and then keep things going from there. So what are we trying to get to here? Well, we haven't really even said what's been done yet, but I do want to highlight sort of what my intention in this presentation is. This is another instance in which we've had to add support for some new functionality in the form of a new type. We'll get into that in just a moment within the driver. So I wanted to sort of document and sort of a chronicle for describing that process from a driver perspective, so that we have this here in case we ever have to do it again, or in case people want to do it on their own by modifying the driver source. That's always an option. All of the drivers are referenced are open source, so you're free to make whatever implementations and modifications you'd like and get your functionality as you wish. But I also wanted to highlight some of the, how do I phrase this? Some of the design considerations associated with the driver. Not everything, it's very, very easy to look at the drivers and think this is simply a technical question of putting bytes together and shipping them over a wire and then reading those bytes off and generating from them. But there is also a number of design considerations that go into that because you are presenting an API to users and you have to think very seriously about how you want to do that and how you want to expose some of that information. So we're gonna touch on some of those notions as well as we kind of move along here. But those 2 things are kind of broadly what I'm aiming to get out of this talk. All right, so what is a vector anyway? It is an object that has been added into Cassandra, and we'll get to which versions in a moment, which has a couple of these features, or a couple characteristics, and I list those characteristics up here. I swear I have a quote from Jonathan Ellis somewhere that actually lists these properties, but I cannot for the life of me find it. So I'm going to present them for purposes of our conversation as a framing device, and you'll have to take my word for it. These are basically fixed length constructs. They consist of elements, all of those elements are of a common type. So vectors do not have, we don't know, none of the strings and ints and combine, they are all of a common type. And they also don't allow nulls. And this, you can think of this very similar to, for those of you who are familiar with Java, these sound very, very similar to Java arrays. We'll come back to that in a moment. But that's what we're talking about, broadly speaking. All right, so why are we talking about this at all? Vector support was originally being discussed, and somebody's been referenced in a number of talks here in the Cassandra Enhancement Proposal 30, which there's a link to for those who want to download the slides, which originally proposed the idea of implementing vectors backed by storage attached indexes. We originally had, this support was originally rolled out and made publicly available via DataStax Astra, via the hosted Cassandra offering that DataStax makes available. And as you all have been hearing over the past few days of talks, that support is also now coming to Apache Cassandra 5 itself. Yes, woohoo, we all have a great party for that because that is awesome. But our initial driver support was intended to support DataStax Astra with the intention that we would eventually support Apache Cassandra once it stabilized its implementation of drivers 5. The conversation was not exactly like, but not dissimilar to, hey, we're going to be releasing this thing out. Can we get driver support? And if we can't get it tomorrow, could we get it the day after tomorrow? So it got done pretty quickly, but it got done reasonably well and has been implemented so far. I don't have it on this slide, but I'll mention now that we do have native driver support native vector support in 3 of our drivers right now, the Java driver and the Python driver, and subsequently it's been added to the Node.js driver as well. So each of those 3 drivers already include native support for vectors. All right, so how do we implement this? And we're going to go a little bit under the hood here, so bear with me. Again, I'm sort of wanting to document this process so that this serves as an instance. Vectors are implemented via custom type. I'll ask generally if folks are familiar with the concept of a custom type in Cassandra. Is that resonant for people? Okay, good. I'm getting good nods. The really nice thing about implementing vectors in this way is that we don't need a new protocol version, because a new version of the binary protocol is a really big deal. It entails a lot of changes to not only the drivers, but also servers as well, and administration costs. It's very, very intrusive. Sometimes it's necessary to bring new functionality, that's life, but adding a new data type ideally is not one of those instances. It doesn't necessarily drive a new protocol version. It can be included in subsequent protocol versions, but it shouldn't drive one itself. And as we mentioned here, we actually do have some precedent for the way this has been approached. I don't know, for those who might remember, but the earlier version of the protocol, just before, or currently on protocol version 5, protocol version 4 introduced the notion of a duration type that was supported by the servers. And that was originally implemented as a custom type in a way very similar to what we're going to describe here. And it was subsequently elevated to a first level type in the new version of the protocol version, which is protocol version v5, which is the version that is supported by Cassandra 4. So this is not the first time this process has been done, but it gives us a rough idea of kind of where we're at. Cool, all right, so what does this look like in practice? We'll take a simple example, the process of iterating over the rows and results. That's something everybody has done before. And now we're going to get into some of the row level messaging, because that's really what the driver deals with in large part. It implements this at a messaging level, or implements support for the messages involved in processing them and evaluating them. So rows are returned in a certain kind of result message. It's a very specific message, which includes a format. I can go into the format here if people want to see it, but that result message. Oh, sorry. There we go. That result message includes a set of metadata to provide additional information about the data in each of the columns that are in the rows that have been returned. And included in that metadata is a notion of call specs. This is lifted almost entirely from the binary protocol spec, which talks about, I won't read it all to you there, you can see it all there. But it talks about this notion of an identifier for the type of the column that is provided, and the call spec defines that. For types that are supported as have full support within the protocol version, there is a unique integer identifier that will identify them, 001 for, I forget which one is, but for say ints, 2 for floats, et cetera, et cetera. For custom types, the call spec, which is a pair, is an integer tag in the string identifying it. The integer identifies that we are dealing with a custom type, but the string then subsequently defines what the actual type is to the driver. That's what the driver looks at to know kind of what it should do. And we have an example here to see kind of what this looks like for the type I referenced earlier, for the duration type, which was a custom type in protocol version 4, but was elevated to a full type in v5. This is what the driver will actually see when it goes to parse this result message that it gets back from the server. And it has a large infrastructure to parse these types and to understand what to do with them. So for vectors, this looks a little different. This is an actual extracted custom type that we get for a vector of size 3 of floats. Notice anything different? we now have params. We didn't have params before. This is the first instance of an actual custom type which includes parameterized types, in which we don't simply say, hey, the parameterized type is a date type or is a duration type, but now it's a parameterized type. This isn't new for the type system within Cassandra, to be clear. We've had the notion of parameterized types for some time in the form of lists and sets and maps, but we haven't had to deal with them in custom types at all. So implementing support, the first task in implementing support for vectors was to make sure that our parsing infrastructure for the custom type handlers to handle these types of type streams could handle the notion of parameterized types and process them accordingly. Took a little while to get that down, but not a big deal. So we got that done. So that's it, right? We do parameterize custom types and we're done and that's it. Well, not exactly. We also have a second type of type names, or of type specification, which are available within Cassandra, introduced in Cassandra 3.0. I meant to look up the JIRA for where that was, and I did not find it. But it's used within the system tables, and it's sort of a simplified, shortened version of the string that you just saw earlier. So instead of this long, lengthy Java-ish class name that we have before, we now have a much smaller version in the form of, as you can see, list and list float. So our much larger version of list type and float type reduces down to list and float. Vectors are actually implemented on the server with this similar notion. So when one goes to look for vectors and sees them, then you will actually see this. This is primarily implemented within the schema tables. So the drivers you wouldn't necessarily hit a problem with this from regular usage of the drivers. But if you did, say, want to go to the metadata that is provided by the drivers and look at any type information that is within there, you would immediately hit some exceptions for being unable to parse this notion of vectors. Oh, sorry, I jumped ahead here, sorry. Yeah, it works for vectors too. So we have the simplified notion of types in the form of vector and float 3 that we see within our schema tables. So we are required to make sure that we can handle this. This is a little better than the previous case because the types in question here already support parameterization. We use these simplified types in the schema for some of the collection types I referenced earlier, some of the types that are already parameterized, things like lists and maps. This simplified syntax is already there. So many of the type parsing machinery within the drivers already support this. We just have to extend it to make sure we can deal with vectors. So, okay, cool. Here is a very specific example to show precisely what I'm talking about. This is a table that has been created, which includes a vector type that we want to retrieve these operations on, and a query underneath to show the schema tables provided by Cassandra so we can see precisely how those types are rendered. Now, this is actually very similar to the queries that are done by the driver when it connects to the server. One of the things that a driver does when it initializes its connection is it queries all of the schema tables so that it has some notion of what the tables, key spaces, and columns and types for those columns are at connection, or that is for what it's dealing with. Cool. All right. So now we're done, right? Like we've added support of parsing for both kinds of this. Surely that's it. Of course, not quite. So we still have to be able to read and write data in the format that we're getting from the server. So the implementation for this varies pretty widely across the drivers, and I'd like to take just a brief digression here to talk just about a little bit of history. In the past, we have largely had discrete teams for handling all of the various drivers that DataStax supports. We had a driver for Java, a driver for Python. The teams would collaborate on sort of higher level goals and general principles, but didn't necessarily worry about implementation level details. That was left largely within team. The result and the key update or the key upshot here is that the internals of implementing this can vary considerably across the drivers. So don't assume that when you implement support for this in one driver that you will simply find a parallel implementation in the other drivers. You very definitely will not. We'll make that kind of concrete here. I'll just run through a couple instances so you can kind of see what I'm talking about. This is what Serde looks like for the Java driver. It actually has a third-party object in the form of a codec who is responsible for serializing and deserializing objects. Each type has its own type codec, in some cases multiple type codecs, that are responsible for turning bytes into objects and objects into bytes. Those are implemented separately. This is a extremely simplified version of the codec interface, but it's enough to give you the idea. Python does it differently. Python actually has representations for each individual type that we have, but the types are responsible for serializing and deserializing themselves. So we have an example here for duration type, but you see that the type is responsible for saying, given a set of bytes, create myself and the inverse, both with static methods on the classes that define them. I'm not saying that any of these are preferred over the other. That's not my intention. My intention is merely to point out that there is a significant difference between how each of the drivers approach this problem. Last, we have the last driver to get vector support, the Node.js driver, which kind of does away with all of this and just has some functions for doing decoding and encoding. There's actually an encoders file within the driver which has a whole host of encode functions for all of the types that you can imagine and a whole host of decode functions for all of the types that you can imagine. So in each case, you can imagine what adding vector support for each of these drivers involves, but it's different for each of them. One other thing to consider, and here we get into something of the design consideration of this. This is not really a technical question. This is, well, it is a mixture, I should say, of both a technical question and a usability question, which is we also need to expose the data that we're getting in some way in a type within the programming language that is meaningful for that system. So what does that mean? If we want users to do queries on rows and get back data out of that, what type should we give them? It should be a type that is meaningful within the system that they have. But that involves a lot of judgment about what is really the right way to do that. And here we get into sort of some of the principles that have guided most of the driver implementations over time. In general, the drivers try very, very hard to reuse as much as possible native types within the platform. You don't see within very many of the drivers very often, there are certainly exceptions to this. This is not a blanket rule. But you do not see instances where the drivers implement a new float class instead of just giving you back a float. That is very much by design. It is much easier for developers and engineers to reason with floats that they are already familiar with from having worked with floats in Java or floats in Python than having to learn about the functionality of your cool new float class that does all kinds of neat things that they don't really care about. That's something we do very much by design. Now, as I say, that is not a universal constraint. We do not apply that universally because it doesn't always work. I cite an instance here of the Java driver not reusing what seems to be a very natural mapping for duration because of differences in implementation that actually prevented that. So unfortunately, we had to have our own duration class. That's just life sometimes. You have to deal with that. Why this matters more than you might think, because the drivers there are certainly a number of situations in which the drivers will try to infer types based on what is passed into it. This happens a lot with, say, creating a SQL statement that accepts arguments of just some random type of data type from the user. We're then tasked with trying to find some way to convert that data type into what we need based on the schema. But that means that the way this is set up, once a native type is assigned to an underlying SQL type, they don't get reused, because you want to know that when you see a type of, say, a float type, that you know that this codec will be used to handle that float. So you don't wind up reusing those cases. So you want to be very judicious about assigning codecs for very common types, assigning codecs to handle very common types to situations where they will actually make sense and not be reused. And we'll see an example of that come up here in just a moment. So here are the decisions that were actually made with respect to how we expose vectors for each of the three drivers. Now let's get into Java is sort of the example that I wanted to refer to earlier with respect to the reuse of something that is very common within the language. The very natural mapping for a vector based on the criteria that I defined earlier is to a Java array. It has very, very similar properties and could very naturally map to a vector as it stands. However, again, once we map a given type to the SQL type, we then don't use that for other situations. When we see an array from that point forward, we would try to make it a vector. And we may not want to do that for a new type like this that is just sort of catching on. So I decided, given that situation, to not use arrays for the representation to and from vectors and to represent them via a new custom class SQL vector. This was a difficult one because I was very tempted to go with arrays, but in the end, it seemed easier to have a custom class to handle that. And that class actually supports the idea of being able to easily move back and forth between arrays, but it is not itself an array. Python is less of a concern. Really, we're helped out quite a bit by the dynamic typing and basically return something that's seekable and that's broadly workable for what we need in Python. Node.js was more of a challenge because, again, our implementation across the drivers is very distinct. So in the Node.js case, we already had arrays taken care of. The arrays had been mapped earlier to the notion of lists. So on a Node.js driver, if you pass in an array of elements, that will get converted to, or the type system will try to convert that into a list before sending that off in the SQL query. So we couldn't use that. That was already taken up. Fortunately, I discovered that we had a relatively new-ish, or at least new to me, I had not come across this before, type in JavaScript called the numeric typed arrays, which actually match very closely, again, to the notion of numerical arrays in other languages. And they had and maintained most of the properties that we have defined for vectors originally in the earlier slide. So that's how this is represented for Node.js. It's a little bit of a change because not everyone's familiar with typed arrays, but oh, hello, what is that? Go away. All right. So now we're done, right? We've done all kinds of type parsing. We've done serialization. Surely we're done. Yes, fortunately we're done. So I provided this here as a summary. This is how I've included this to reference a summary of the set of things that need to be done to perform a task like this. This includes the notion of type information. It includes the serialization, deserialization operations. And again, the very important notion of considering how you expose this within a language and how you make this available. So these goals right here sort of represent the sort of concepts that one has to deal with in dealing with this in a language. That's cool, but where's the new stuff for vectors? The nice part about this is that we actually don't really need one. Because of the way vectors were implemented both in the server as well as implemented within these mechanisms within the driver, they fit within the existing driver APIs. So as long as you are aware of the types that are involved with either submitting or reading data into the driver APIs, you will be able to use everything as they stand and not really have to change very much. This was, again, very much by design. We didn't want vector-specific operations or vector-specific APIs that would potentially confuse things. So as much as possible, we've tried to preserve the existing functionality. All right, so cool, we're done. Anything else to do? Yeah, we do still have some things to do. The original implementation, as I mentioned for this, was designed to support DataStax Astra. DataStax Astra includes support for vectors of a single type, or at least it did in our initial rollout. That was vectors of type float, and that was all we had. Apache Cassandra 5.0, which is coming out very, very soon, and is much more expansive in terms of the set of types that it will support within vectors. So our drivers need to make sure that they can work with vectors of many, many different types in order to support everything that users of Apache Cassandra 5.0 will want. And we have some work to do there to make sure that we're okay on that front. We also have a lingering problem with respect to when we get to that process around the serialization for variable size types. I mentioned that we can support floats right now, and we can pretty easily support, given the current implementation, types that are of a fixed size, so floats, integers, things like that. But when you start getting into types of a more indeterminate size, because of the way the serialization works within Cassandra 5, we have more of a problem as things stand right now. So we have some work to do here in order to support this. This is all represented within the JIRA referenced here. So if you want to find out more about that process and sort of what that effort looks like, you can find out some additional information at that spot. And I believe that is all I have. I have some time left here for questions if anybody has some. Oh, yes, sorry, go ahead. Sorry, say again?
So I tried the same thing for the node data.
Uh-huh.
For Python, it was fine. For Java, I was able to retrieve the vector. But when I tried with the node, it was giving me some decoding error.
Really?
Yes. I did the ticket also.
Check with me after the talk, and let's see if we have a ticket for you already. If not, then we'll see if maybe we can submit something. I'd like to see the sort of the code in the area you're actually seeing. That was the most recent version on NPM. That's the one you were using. Yeah. Yeah, it's tested. The current version of Node, the NPM version, or the version that we last pushed to NPM, supports. I believe it officially supports 18 and 20, but it also works for 16 kind of unofficially. But it should work pretty well for 16. So any of the major LTS versions of Node should be supported pretty well with that. So. But check with me after, and we can talk about that. Any other questions? Anybody have any questions about anything we talked about?
I have a previous question.
Oh, sorry.
I guess same thing is one number. There is one limit, hard limit, 1,000. When I try to retrieve the vectors, there is a limit how many items you can retrieve when you're querying the, let's say, when you're using the vector.
So the vector, the param in the vector case, where is it?
Yes, from the server side.
Oh.
Limit 1,000 is the most you can retrieve. Because it all has to be in memory, so you don't want to on the server. So there's a hard cap on the maximum number you can retrieve.
Can I increase it? Let's say if I have the memory.
No. I mean, you can go build your own Cassandra and change the number. There may be like a dash D or something to let you change it. I don't remember, but it's definitely, yeah. That's a server side limitation, not the drivers.
Stefano, did you have something else?
Just a curiosity. So Python has no notion of double versus float. So I wonder, I guess, where exactly a possible loss of precision
Yeah, those. So most of the native numeric types in Python are set up via packing or via implementations off of Packer for.
That's where the excess precision is lost.
Yeah, that's what OpenStruct gives us. So I mean, it's just kind of the life we live.
Typing goes that far.
Right. Yeah. So that's what we have to live with in that case. Yeah. Yeah. All right. Anybody else? Oh, yes, in the back. Sorry. Same situation I mentioned earlier. Check with me after. We got to make sure we have time for the next speaker here. So check with me after, and we can talk about that some more. But we'll see if we can get you some information on that. Okay. Oh yes, go ahead, down in front.
The C# driver. What's the plan?
Right now, there are no plans to add vector support to either C# or C++. If you would like to see that, I would encourage you to either get in contact with DataStax support or post something on the mailing list and sort of indicate that that's a desirable case. You could also file a JIRA as well. We have a lot of those, so I'm not going to make any guarantee. I can't make any guarantees on any specific ticket getting addressed at any specific time, but that would be certainly a good way to get it into the conversation and have it discussed.
Also, Apache license patches accepted.
What Jeremiah said. Like we've laid out an excellent example here to give you a lot of guidance as to all the things you would have to implement in order to support it. So I'd love to see that, yeah. And our C# developer is wonderful, so yes. Fortunately, they don't let me anywhere near the C# code, so that works out well for everybody. All right, anybody else? Any other questions? We're wrapped up, I think, on time. So if anybody else has any questions, please come down and check with me. And I think that's it. Thanks, everybody.
This is the last session of the conference, so thank you for everyone participating to this point. As you can tell, I am not a Tissin Matthews. Tissin has actually, unfortunately, caught the flu and he missed his flight this morning. And because I was working with Tissin very closely in the deployment of generative AI, as well as I'm actually very passionate about elderly care from previous startup work that I've done, I had the honor to be able to give this talk today. So SkyPoint, to give you a little bit of context about SkyPoint, they're an AI platform that helps the senior care industry. And what they basically try to do is give access to information around elderly care, and it's primarily geared towards nurses, doctors, et cetera, et cetera. Now the question is, why is this so important? Like, how exciting could elderly care be? Well, the number of individuals that need elderly care is going to be doubling by 2030. The budget is $1 trillion a year in the United States alone. Just for some context, the entire US defense budget is $800 million. So what's going to happen when we have double the number of elderly in the United States? Is our budget going to go up by 2x to $2 trillion? No. We're going to have elderly being put out on the street. There's going to be a lot of poverty, a lot of pain. The good news is, in the elderly care industry, 70% of the costs is actually on administration. It's not on care. And I know you're all shaking your heads. What do you mean by administration? Well, things like figuring out how to do my insurance payments, things like scheduling new nurses to come to take care of the elderly, all those kind of things. There's about 70% of waste that really IT should be able to get rid of. And generative AI is extremely important because when I actually tried to tackle this problem when I was trying a startup company through mobile apps, it turns out nobody wants to do that. It turns out that nurses, elderly, children of the elderly, et cetera, they all communicate via text. It's all actually human interaction. So the only chance that one actually has to get rid of a lot of these costs in elderly care is around generative AI, in my opinion. So that's why this is so important from a societal standpoint. This is probably the most, I think, there's nuclear war, climate change, and then the secondary effects due to the population inversion. So this is probably, in my opinion, the most impactful way to use generative AI. And so what SkyPoint AI does is an end-to-end life cycle for your data. So all the data, they basically have a big database of all the different data related to healthcare. It's a lakehouse at the core. And then the Copilot, the AI Copilot, allows you to chat with your data. And one of the things that they've been working on, that SkyPoint has been working on, is creating Microsoft Chat Copilots. So these are Copilots that are on top of your AI-ready data. They leverage a combination of, they leverage a lot of the, they try to unify all the data. It's very industry specific. And they do actually something called a lot of fine-tuning of the AI models. So that with ARLA, HF, et cetera, et cetera. From an architecture standpoint, SkyPoint leverages a combination of structured data, primarily in Databricks on top of Azure. And then they also leverage unstructured data that is stored in vector databases in AstraDB. To give a little bit more context to this, for example, in the case where they're querying structured data, they would take the data and then they would leverage a process called self-reflection. So the LLM would take the data and then start saying, okay, what do I do? I need to answer this question. So let's look at the different over time. Let's look at the different tables there. So there's actually underneath the hood, it makes an API call via the tools API within LangChain to the Unity catalog. This is the Databricks Unity catalog to collect information about what tables there are. And it would identify, the LLM would be smart enough to identify which particular columns to use from which tables. Then there's a process, once we have collected the right schemas, the right tables that the data is from, then there's a process of generating the SQL statement. And then they would leverage previous examples called few-shot prompting in order to generate the SQL statement. So in this case, the LLM realizes it needs to join the employee, attendance, and group by role. So underneath the hood, this kind of method, there's a method called React. This is a reasoning action. It's a paper published by Google in 2020. And this is very similar to, if you guys were in my previous talk, the action perception loop. So React stands for reasoning action. And in order to generate the SQL statement, they do a couple of things. They pull in the data model into, when they do the prompting, they pull in the data model. They use dynamic few-shotting. So this is creating the natural language SQL statements. And this is particularly useful when you're trying to do joins and group bys. They do metadata annotation. So what happens is that in the Unity catalog, where they have all the table schemas, they're able to provide extra information, such as what does this table mean? What do these columns mean? How are the column information related to each other? Then they use something called structural decomposition. So this is the idea of splitting up a question into multiple questions. And then the last but not least is something called self-reflection. So self-reflection is a technique to see if the generated SQL statement answers the original question that was being asked. And underneath the hood, there's also a whole bunch of enterprise features. Namely, they've implemented RBAC and observability, RBAC, access control, and then observability to make sure that these things are, the answers are being surfaced right. So diving a little bit more into the SQL agent, this is a LangChain particular feature. The few-shotting, so for example, if there's a question, say, what is the average rating of a community Morris house? It's able to figure out what is the right columns, leveraging the metadata to identify the right columns, and then generating this average, it's able to generate this particular statement. As I just talked about, self-reflection is able to allow you to see if the end query matches the original question that's being asked. So what about structured data? So structured data, what they do, what that does underneath the hood is that, let's take a look at this question. What is the leave policy for new hires? One of the methods that they use is this called multi-query generation. So we would take one particular question and decompose it into multiple questions. So for example, what is the leave policy for new hires? Then it could be broken down to what is the new policy for new hires? So actually, that's just the original question. What is the leave policy for new joiners, which is similar to new hires, right? But it's just an extra question. And then what is the absentee policy for new hires? So it generates 3 questions at one time and then calls one or more vector database tables. And then after it gets back the response from 3 questions in a row, the LLM is able to summarize the answers for all 3. So RAG is being done on top of PDFs, text documents, et cetera. They leverage a lot of document annotation. And one of the things they do is actually they use a lot of fine tuning. So once you have enough history built up of making these kinds of queries, and they look at the thumbs up, thumbs down, they would be able to figure out what kind of data they can use to fine-tune the models, such as the OpenAI models. Then there's also this idea of contextual compression of algorithms. And what this is really leveraging like fine-tuning again to skip some of the steps that, because these are multiple steps, they could use fine-tuning to actually just skip some of the steps. Another way that you can use fine-tuning to skip steps is that, let's say, for example, in this case, there might be a step of having to go out to the database to fetch the catalog of all the schemas. One can actually take all the catalog of the schemas, fine-tune the LLM, so the LLM already knows what schemas there are in the database. So you can skip the step of having to go out to the database to grab a schema. So there's a lot of like nifty tricks that one can do to really cut down on the latency. All right, and then the last point is the combo prompts. So this allows you, so the most powerful ones are something like this. Like this is a fairly complicated query. It's asking you to do a lot of different things. And they leverage underneath, in order to construct this query, the answer for this query, it needs to be broken down into both structured and unstructured data. And so one of the very big concepts in retrieval augmentation is the idea of doing planning. So they're doing a plan, and they want to make the plan be able to be parallelized so that they might be able to fetch data from multiple places all at once. And there's different access patterns that are kind of, there's different ways to actually get the data. One is you do unstructured RAG with structured querying. When I say structured querying, it just means you're asking a structured question to the LLM. You could do unstructured RAG, sorry, this is supposed to be unstructured RAG and structured RAG. Structured querying plus structured querying plus structured querying plus unstructured RAG. So there's many different combinations of the ways that you can actually you collect your data. And so, for example, this particular use case, they decompose it into these several questions, these several plans in order to fetch all the data at once. And I think this is probably the ultimate in terms of doing Q&A, because you're leveraging the combination of the data that's structured as well as unstructured. And I think this is very exciting for Cassandra, because majority of the data being stored in Cassandra these days is structured data. So the end conclusion is that SkyPoint, it incorporates multiple pillars into enterprise AI. Those pillars are accuracy, configurability, reliability, governance, security, and observability. So that's a good example of a production AI system that leverages fairly sophisticated generative AI and advanced RAG techniques. Thank you. Any questions?
How long has it been in production?
It's been in production since June, end of June. Yeah, end of June.
Are they starting to be able to measure benefits and
Yeah, they've been able to measure benefit. The question was, are they able to measure benefits? And the answer is yes. Their early customers are finding massive time savings through this. In fact, it's shocking how much time they're saving. And I think that's another point, is that, you know, if you are doing saving of time to the bottom line of employees who are fairly high cost, like nurses, you know, they start at $50 an hour, right? And if you can save 1 hour of nurse time just by providing these kind of generative AI apps, you can start charging based on a certain percentage of what the nurse's salary per hour is. So I think this is kind of, from a business standpoint, very different than, let's say, the other technologies like mobile or business reporting. Any other questions?
Yeah, so in
I think the hardest part that they dealt with was hallucinations. And they basically, like, so SkyPoint, they threw everything at it. Every single technique possible, they've tried it out. And so there was a lot of experimentation. The area that I think they have the most opportunity is this combining structured data and unstructured data. I think that's kind of the holy grail. It's something that they're still working on, but if somebody can crack this, that'd be very, very powerful. The other part that was really hard was to get under the 5-second SLA. So a lot of these techniques are multi-step problems, right? So for example, taking this one query and turning it into 3 queries. Previously, what they did was they took this one query and they used a technique called FLARE. This is forward active retrieval generation. And what the FLARE algorithm does is that it does RAG, but it looks at the probability of the tokens being generated from the LLM. And if the probability is low, it would cause the system to try to re-ask another question. So meaning that you can use the LLM to actually figure out if it's unsure about itself. Now, that sounds great in theory, but what happened was they found that there was too many round-trip costs, and that instead, it's better to take one single query, turn it into multiple queries, and then do parallelization at one time, which is actually why they moved off of Azure Cognitive Search onto Cassandra, is because they wanted to have a lot of this parallelization capability. So it's balancing that was the hardest thing for them to do. Any other questions?
So in, let's say, it's a platform, so I think different companies use their platform. How many data sources, different data sources are we talking about to be able for it to know which one to go to? I must probably miss that part of it.
Yeah, actually, I don't know. But I looked at their schema, and they had hundreds of tables. I looked at their Databricks schema, and it was hundreds of tables. It was like a massive ER diagram that looked too small on the screen in Zoom. So it's a lot. Okay. And actually, that's the point, too, is that one of the things that was fairly surprising was they did add a little bit of annotations to their tables, but they managed to get high enough results. Just even without annotations, they managed to get high enough accuracy on the results. So they're, depending on the customer base, they get between 85 and 95% accurate results, like thumbs up, thumbs down. Any other questions? All right, let's then have drinks. Thank you, everyone.